Welcome to the Sleepy Academy. I'm so glad you found your way here tonight. This is a space designed just for you, a place to let go of the day, to unclench your jaw, relax your shoulders, and simply drift. We believe that learning something fascinating, when done softly, is the perfect pathway to deep rest. If you find comfort in these quiet explorations, please take a moment to gently tap the like button and consider subscribing to join our growing community of sleepy learners. We would love to have you with us. Now, settle in under the covers, close your eyes or just soften your gaze, and let's begin our journey outward. Beyond the familiar constellations that guard our night sky, there exists a quiet brightness. It doesn't demand your attention, it just waits there, a soft glow in the deep dark. It is nothing dramatic, nothing insistently flashing, and yet it extends outward on a scale that is difficult to truly wrap our minds around, a scale so grand it becomes peaceful to contemplate. Tonight, we are going to gently explore this vast space. We are going to ask a simple question and drift slowly toward the answer. How huge, really, is our neighbor, the Andromeda Galaxy? That subtle glow, visible to the naked eye on a perfectly clear, dark night, has been known for almost as long as humans have looked carefully at the sky. For most of history, before we had powerful telescopes, before we truly understood what we were seeing, it was thought to be a simple cloud, a distant, sleepy smudge of unresolved light, fixed quietly in place among the sharper stars. To the ancient observers, its apparent size seemed modest. Its boundaries appeared gentle, contained, like a soft little island of light tucked away in the cosmos. There was nothing about that faint, fuzzy patch that suggested how truly enormous it really was. It was a sleeping giant, waiting to be understood. Modern astronomy has learned to be very wary of initial appearances. As the centuries passed, our eyes grew sharper. We built telescopes that could peer deeper into the quiet corners of the night. These instruments learned to be patient, staring at the same spot for hours, drinking in the faint light that had traveled for millions of years. And slowly, layer by layer, Andromeda began to reveal itself. It wasn't just a cloud. Where we once saw only darkness, long exposures uncovered faint stars drifting far beyond the bright central swirl that catches the eye. We began to see ghostly wide-field surveys tracing faint stellar streams stretching outward like ripples on a calm lake, echoes of ancient movements that happened long ago. We began to measure how stars and smaller galaxies move around it, dancing to a silent tune which hinted at immense amounts of mass extending far past anything that actually shines. With every new look, with every moment of patience in observation, the galaxy seemed to breathe out and expand. It didn't grow suddenly or dramatically, it was a quiet, steady growing in our understanding. Its edges, which once seemed so clear, began to soften. The outline blurred, dissolving gently into the surrounding velvet of space. What once looked like a neatly bounded island of stars became something far more diffuse, more expansive, and wonderfully harder to define. Astronomers gradually discovered that asking, "How big is Andromeda?" is like asking, "How big is a whisper?" It depends entirely on what you are listening for. Are you measuring the luminous disk that first caught the eye, that bright swirling center? Or are you measuring the vast halo of ancient stars surrounded like a soft blanket? Or perhaps are you measuring the invisible, silent structure inferred through gravity alone? Each way of looking tells a different, sleepier part of the same long story, and each one expands the galaxy well beyond its familiar appearance. Some of the most significant discoveries about its size came almost unintentionally, like finding something wonderful when you weren't looking for it. Surveys designed to study nearby stars kept finding stars belonging to Andromeda where none were expected to be. Projects meant to refine distances instead revealed vast structures hundreds of thousands of light years across. Even the deep black space between Andromeda and our own Milky Way turned out to be less empty than once believed, threaded with overlapping regions that challenged the whole idea of where one galaxy ends and another begins. Over time, the questions changed. We stopped looking for a clear, sharp edge. Instead, it became more about understanding influence. How far does its sleepy stars wander into the dark? How far does its silent gravity reach? How much of the empty space is quietly shaped just by its immense presence? This isn't a story that ends with a single number waiting at the end. It is a slow, gentle unfolding of perspective, shaped by decades of quiet observation and refinement. It is a comforting reminder that in astronomy, size is rarely sharp, and boundaries are often soft suggestions rather than rigid lines. Tonight's journey is about how Andromeda grew larger in our minds, how careful measurement transformed a small patch of light into one of the most expansive structures in our local universe, and how, in the process, it taught astronomers something subtle and calming about scale itself. So, settle in deeper. Let your mind expand gently outward, just like the galaxy. Let's drift back in time for a moment, back to the beginning of the 20th century. At that time, Andromeda did not yet feel enormous to us. It didn't even feel like a separate galaxy. Through the brass telescopes of that era, it appeared as a soft, elongated glow, a misty patch of light stretched gently across the lens, brighter in the center and fading softly outward into darkness. Astronomers referred to it as the Andromeda Nebula, grouping it with other cloudy, indistinct objects whose true nature was still unclear. Some thought these nebulae were nearby collections of gas and dust forming new stars right here within the Milky Way itself. Others suspected they might be something far larger, far more distant, but there was no way to be sure. The problem wasn't a lack of imagination, it was simply measurement. Early telescopes were limited by the quality of their glass, by the shimmering distortion of Earth's own atmosphere, and by the sensitivity of the human eye. Even when photography began to assist astronomy, the earliest photographic plates could capture only the very brightest regions of an object. Anything faint, diffuse, or spread too thin across the sky simply failed to register on the film. The darkness swallowed it whole. So, when astronomers pointed their instruments toward Andromeda, what they recorded was only its most obvious feature: a bright central region, a smooth, glowing core, a disk that seemed well-defined and comfortably contained. The outer reaches, where light thins and stars grow sparse, remained invisible. To those early observers, Andromeda looked modest, larger than most other nebulae perhaps, but still something that could plausibly fit inside our own Milky Way. Its apparent size on the sky was measured in angular terms, how wide it appeared compared to familiar reference points like the Moon. By those measures, it seemed manageable, finite, knowable. That impression shaped all the early estimates. Photographic plates taken in the late 19th and early 20th centuries captured Andromeda as a flattened oval of light. Astronomers traced its visible outline on these plates and assumed that what they could see represented most of what existed. This was a reasonable assumption at the time. After all, if something held stars, and those stars emitted light, and that light did not appear on the photographic plate, how could it be there? The answer, it turns out, was patience. Photographic plates required long exposures. Early ones could take hours, sometimes entire nights, just to collect enough faint light to form a clear image. Even then, they struggled to pick up faint stars and regions where the brightness was low. The human eye peering through an eyepiece fared no better. Our vision adapts poorly to subtle gradients in the dark. Where light fades gradually, the brain often just decides that nothing is there at all. As a result, Andromeda's bright core dominated everyone's attention. The outer reaches were assumed to taper off quickly and disappear. Its size was underestimated not because astronomers were careless, but because the universe was quieter than their instruments could hear. The question of what Andromeda truly was came to a turning point in the early 1920s. Careful, patient observations of individual stars within that glowing patch revealed something extraordinary. Astronomers found that some of those stars changed their brightness in a very predictable way, like slow, breathing lighthouses. This allowed their true, intrinsic luminosity to be estimated. By comparing that intrinsic brightness to how faint they actually appeared in the telescope, it revealed their distance. The numbers were a soft shock. They were unsettling. Those stars were far too distant to belong to the Milky Way. They lay well beyond its boundaries, separated by a gulf of space so vast it forces your mind to slow down just to think about it.
With that dramatic realization, Andromeda was no longer a nearby cloud. It was an entire galaxy, comparable in scale to the Milky Way itself, containing countless stars of its own. With that realization, Andromeda suddenly grew. Not physically, of course, it has always been huge, but conceptually in our minds. It was no longer a small structure tucked inside our home galaxy. It was a separate island of stars, adrift in the vastness between galaxies. Even so, its size was still underestimated for a long time. Knowing that Andromeda was a distant galaxy did not immediately reveal how large that galaxy truly was. The same observational limitations remained. Telescopes still captured mostly the bright inner disk. Photographic plates still missed the faint outskirts. Astronomers now understood that Andromeda was vast, but they still did not know just how far it extended into the dark. Early size estimates focused on the luminous region, the beautiful spiral structure where stars were densely packed and easily visible. This region appeared well-defined, with graceful arms curving outward from the center. Beyond those arms, the light seemed to drop away quickly. It was natural to assume that the galaxy ended not far beyond that point. This assumption shaped diagrams, textbooks, and our mental images for decades. In reality, relying on those early measurements was like judging a vast city by looking only at its bright downtown area. It was bright, crowded, and easy to see, but hardly representative of everything that lies beyond. The suburbs, the quiet outskirts, the spacious regions where lights are sparse and distances stretch out, all of that was missing entirely from the picture. The limitations of early instruments meant that Andromeda's fainter stars blended into the background glow of the sky. You see, the universe itself is not truly perfectly dark. There is air glow from our atmosphere, scattered light, and the combined shimmer of countless distant stars creating a soft background noise that hides delicate structures. Against that faint glow, Andromeda's outer regions simply vanished. There was also a psychological element at work. Human perception prefers hard edges. We look for boundaries and clean shapes. When a glow fades gradually rather than stopping abruptly, the mind often interprets the fading as an ending. Early astronomers, like all observers, were influenced by this tendency. Where the image became indistinct, they assumed the object had finished. So, Andromeda was drawn smaller than it truly was. This underestimation persisted well into the middle of the 20th century. Even as telescopes improved, the focus often remained on the brightest, most photogenic parts of the galaxy. Spiral arms, star-forming regions, and the luminous core drew all the attention, while the faint outskirts continued to escape notice. Yet the seeds of revision had been planted. Astronomers now knew that appearances could deceive. They knew that galaxies were not neat, compact objects, but sprawling systems shaped by gravity over immense spans of time. The realization that Andromeda was a galaxy opened the door to a deeper question, one that would take decades of slow, quiet work to unfold. If the bright disk was not the whole story, how much lay beyond it? The early measurements, limited though they were, provided a necessary starting point. They taught a quiet lesson that would echo through future discoveries. What you see is not always all that is there. As instruments grew more sensitive and observations more patient, Andromeda would begin to reveal just how incomplete those early views had been. The galaxy that once seemed modest and contained would gradually stretch outward, dissolving the idea of a clear edge and replacing it with something far more expansive and peaceful. But at the beginning, it all started with just a glow, a soft, misty shape, and a universe that was already far larger than it appeared.
When telescopes finally left the surface of the Earth, Andromeda changed again. It changed not because the galaxy itself altered in any physical way, it remained as it had been for eons, but because our view of it finally became still. For centuries, every single observation of the night sky had been filtered through the restless, shifting ocean of air that wraps our planet. Earth's atmosphere protects us, but for an astronomer, it is like trying to birdwatch from the bottom of a swimming pool. It bends incoming light, scatters it, and adds a faint, permanent glow of its own. Stars shimmer and twinkle, which is beautiful for poetry but difficult for measurement. Edges soften. Fine detail slips away into the tremor of the air. Even the largest, most majestic ground-based telescopes were always listening to the universe through a layer of static noise. Space-based observatories removed that problem in one decisive, quiet step. By orbiting high above the atmosphere, they allowed light from distant objects to arrive undisturbed. What reached the detector was cleaner, steadier, and far more precise. When instruments like the Hubble Space Telescope finally turned their unblinking eyes towards Andromeda, the galaxy did not suddenly become brighter, it became clearer, it became more real. One of the most important differences was simply time. The Hubble Space Telescope was designed to stare. Instead of capturing a quick glance before the sun rose or clouds rolled in, it could remain fixed on the same specific region of the dark sky for hours or even days, collecting faint light bit by bit, photon by single photon. Each tiny packet of light that arrived after traveling millions of years was recorded and added to the rest. What could not be seen in a short exposure slowly emerged in a long one, like a photograph developing in a darkroom, ghosting into view. This change alone reshaped Andromeda's appearance in our minds. Earlier, grainier images had shown that bright spiral disk we talked about, well-defined and elegant, fading neatly into the surrounding darkness. But Hubble's longer, deeper exposures began to reveal stars scattered far beyond that familiar outline. At first, they appeared as isolated points, almost accidental, like dust on a lens. Then, as exposure times increased and patience was rewarded, they formed patterns, streams, halos, extensions that could not be ignored. The visible disk expanded. It didn't happen abruptly or dramatically. It stretched outward quietly, the way dawn light spreads across the horizon before the sun actually rises. Each deeper image pushed the boundary a little farther out, revealing that what once looked like empty black space was in fact thinly populated territory. This process highlighted something fundamental about how telescopes work. They do not show objects as they strictly are in some absolute sense. They show what light allows them to show, given enough time and sensitivity. Bright regions dominate quickly. Faint regions require patience. Andromeda's outer stars are faint not because they are unusual, but because they are spread across enormous distances. Their light is real, but it is diluted against the soft background glow of the universe. It sits right at the very threshold of what we can detect. Hubble was especially well suited to this delicate task. Its sharp vision allowed astronomers to distinguish individual stars in Andromeda, rather than seeing only a smooth, creamy haze. By counting these stars one by one and measuring how their density changed as they looked farther from the center, astronomers could trace the galaxy far beyond its previously accepted edge.
What they found was not a wall. It was not a cliff where the galaxy dropped off. It was a gradient. Star density declined gradually as distance increased. There was no sudden cutoff, no clear line where the galaxy stopped and space began. Instead, the light thinned, softened, and blended into the background. This realization changed how astronomers talked about size. If a galaxy fades rather than ends, then its apparent size depends entirely on how faint a glow the telescope can detect. A brighter instrument sees farther. A longer exposure reveals more. The boundary is not fixed. It moves with our technology. It moves with our patience. Even with Hubble, that boundary remained provisional. As powerful as it was, Hubble still had limits. Beyond a certain point, Andromeda's stars became too sparse and too faint to separate cleanly from the background of distant galaxies and cosmic light. Noise began to compete with the signal. Distinguishing what actually belonged to Andromeda from what lay far beyond it in the deep universe became increasingly difficult. This meant that even Hubble could not see the galaxy in its entirety. That fact is easy to overlook when looking at its beautiful, polished images. They feel complete, expansive, satisfying. But the astronomers working with the raw data were always aware that what they were seeing was a lower limit, not a final outline. The galaxy was at least this large, possibly larger.
This understanding encouraged new ways of thinking. Instead of asking, where does Andromeda end, astronomers began asking, how does its light behave with distance? How quickly does the brightness fall off? How does the star density change? How far does the structure remain coherent before dissolving into the wider universe? These questions shifted attention away from hard edges and towards soft patterns. There was also a quiet lesson in humility here. Every improvement in imaging had so far revealed more galaxy, not less. Each time astronomers believed they had captured Andromeda's full extent, deeper observations gently proved otherwise. This did not feel like failure, it felt like refinement, like polishing a lens. Space-based observatories had not exposed mistakes so much as they exposed assumptions. The assumption that brightness equals importance. The assumption that what fades must be ending. The assumption that galaxies are compact objects rather than sprawling, breathing systems shaped by gravity and time. Light, we learned, does not behave that way. It weakens gradually. It thins. It disperses. Andromeda's visible disk, once thought to be a clean structure with graceful boundaries, turned out to be just the brightest portion of a much larger whole. A luminous center surrounded by increasingly subtle layers, each harder to detect than the last. There was even a touch of irony in this discovery. The better astronomers became at seeing, the less confident they became about defining limits. Clearer vision did not produce sharper edges, it revealed softer ones. Hubble's observations made one thing unmistakably clear. The size of a galaxy cannot be pinned down by a single image. It depends on depth. It depends on how faint a signal the observer is willing to pursue. In that sense, telescopes do not simply reveal galaxies, they negotiate with them. They ask how much light is willing to be shared. They listen longer. They push deeper. And each time the galaxy answers with a little more than before. Andromeda, seen this way, is not an object with a tidy outline. It is a structure that slowly emerges from the darkness, one exposure at a time. At first, Andromeda grew in the margins. It grew in the spreadsheets and the data meant to measure, not in the images meant to impress. As astronomers pushed beyond the bright spiral disk, they began to realize that the familiar picture of Andromeda was incomplete in a very specific way. Telescopes like Hubble could now see faint stars, but only in very narrow fields of view. Each observation was like peering through a keyhole. You could see deep, but you couldn't see wide. What was needed was not just depth, but breadth. The next shift came when astronomers decided to stop focusing on the beautiful center and instead map the dark, quiet space around it. Wide-field surveys changed the question entirely.
Rather than asking, what does Andromeda look like, they asked, where are its stars actually hiding? One of the most influential of these efforts was the Pan-Andromeda Archaeological Project, a project with a name that hints at digging into the past. It was designed not to take a single beautiful image, but to systematically scan a vast region of sky surrounding the galaxy. The goal was deceptively simple: identify individual stars that belong to Andromeda, even far from its bright core, and see how far outward they extend.
To do that, astronomers relied on a particular kind of star, red giants. Red giant stars are especially useful for this kind of detective work because they're luminous and relatively easy to identify, even at great distances. Their brightness and color follow predictable patterns, making them reliable markers of membership. They are like lighthouses in the dark. If a red giant with the right characteristics appears in the outskirts of the sky where Andromeda sits, it is very likely part of the galaxy itself. When astronomers began plotting the positions of these stars across wide swaths of sky, something unexpected emerged. They kept finding them. They found them far beyond where the disk was supposed to end. At first, these detections were sparse, a few stars here, a few there. It would have been easy to dismiss them as outliers or background confusion. But as the survey expanded and the data accumulated, patterns began to appear. The stars were not random. They formed a diffuse, extended structure surrounding the galaxy. Andromeda had a halo. This stellar halo was not a thin shell or a neat boundary line. It was a vast, roughly spherical distribution of ancient stars stretching far beyond the luminous spiral arms we all recognize. In some directions, red giant stars associated with Andromeda were detected hundreds of thousands of light years from the center. This alone changed everything. Earlier estimates had focused almost entirely on the visible disk, which spans on the order of a few 100,000 light-years across. The discovery of the stellar halo effectively doubled that scale. Andromeda was no longer just a spiral galaxy with elegant arms. It was embedded within a much larger, more diffuse structure, floating like a pearl inside a vast, translucent shell. Importantly, this was not a sudden announcement or a single dramatic paper that changed the world overnight. It was a gradual realization that unfolded as more of the survey was completed. Each new patch of sky added more points to the map. Each confirmation strengthened the picture. The galaxy did not grow overnight. Our understanding did. There was a quiet elegance to this process. Astronomers were not redefining Andromeda based on speculation or theory alone. They were counting stars. They were mapping positions. They were comparing densities. Where the number of red giants declined slowly rather than abruptly, the halo persisted. Once again, there was no sharp edge. The halo faded gradually, just as the disk had, but on a far larger scale. Its stars were old, often older than those in the spiral arms, relics of Andromeda's early history. Some likely formed in the galaxy itself, born in the deep past. Others may have been acquired long ago, pulled in from smaller galaxies that wandered too close and were stretched into long streams by gravity. These streams were another clue. Wide field surveys revealed faint, elongated structures wrapping around Andromeda, the remnants of past mergers. They traced graceful arcs across the halo, evidence that the galaxy had grown not only by forming stars, but by absorbing others over billions of years. Each merger added stars to the outskirts, puffing up the halo and extending the galaxy's reach. This made the concept of size even more slippery. Was Andromeda as large as its disk? Or was it as large as its halo? Or was it as large as the farthest, most loosely bound star that could be found? The answer depended on perspective, but one thing was clear. Earlier measurements had been missing a significant fraction of the galaxy. There was also a methodological lesson embedded in these findings. Galaxies cannot always be understood by looking at light alone. The brightest regions tell only part of the story. The faint outskirts, though visually unimpressive,
often carry the most information about growth and history. In a way, Andromeda had been hiding in plain sight. Its halo was not invisible. It was simply too subtle for earlier instruments and too spread out for narrow observations. Once astronomers widened their field of view and focused on individual stellar traces, the galaxy's true scale became impossible to ignore.
The reaction within the field was not shock, but recalibration. Size estimates were revised, models were adjusted, diagrams expanded. Andromeda's place among nearby galaxies was reconsidered. It was not just slightly larger than once thought, it was structurally more complex. This quiet expansion of understanding also reinforced a broader pattern in astronomy. Every time observation improves, galaxies tend to get bigger. Not because they are changing, but because their faint components are finally being seen. There was even a touch of gentle humor among astronomers. Andromeda, it seemed, refused to stay inside the lines drawn for it. Each new survey extended those lines outward, as if the galaxy were politely reminding observers that it had never agreed to such boundaries in the first place. What mattered most was not the exact number assigned to its size, but the shift in thinking that followed. Galaxies were no longer viewed as compact islands of light surrounded by absolute emptiness. They were recognized as layered systems with bright centers, extended halos, and long memories written in faint stars. By the time the wide-field surveys were complete, Andromeda had become something much larger than a spiral disk. It was a sprawling structure shaped by time, gravity, and repeated growth, a galaxy whose most expansive parts are also its quietest. And all of this had been there all along, waiting for us to look wide enough to see it. For a long time, Andromeda's spiral disk felt like the whole story. It is the part of the galaxy that announces itself most clearly, bright, structured, elegant. From even modest telescopes, the disk reveals sweeping spiral arms wrapped around a luminous central bulge. Dust lanes cut dark curves through starlight. Star-forming regions glow softly, marking places where gas is dense and active. It looks complete, almost self-contained, as if the galaxy has been neatly drawn and carefully finished by an artist's hand. It is easy to see why astronomers once thought this was essentially all of Andromeda. The disk is visually striking because it concentrates light. Stars are packed closely enough that their combined glow stands out clearly against the sky. Gas clouds reflect and emit light. Young stars shine intensely. Compared to the faint outskirts discovered later, the disk feels confident and well-defined. Early measurements naturally focused here. Astronomers traced the visible spiral arms and measured how wide they appeared. They mapped the bright regions where stars were easiest to count. Over time, these measurements became more precise, and disk size estimates began to settle into a consistent range. Unlike the halo, whose boundaries kept expanding as instruments improved, the disk seemed stable. It did not keep growing. This stability gave the disk an air of authority. If something was measurable, repeatable, and visually obvious, it felt reliable. Diagrams of Andromeda in textbooks often showed a tidy spiral disk with little emphasis on anything beyond it. The disk became the galaxy, at least in the popular imagination. But even as the disk's size stabilized, something curious was happening within it. Astronomers began measuring how gas moves inside Andromeda. Clouds of hydrogen gas emit radiation at specific wavelengths that radio telescopes can detect, even when the gas itself is invisible to optical telescopes. By observing how this emission shifts as different parts of the disk move toward or away from Earth, astronomers could measure rotation. This produced what are known as rotation curves. A rotation curve shows how fast different parts of a galaxy orbit its center at different distances. If most of a galaxy's mass were concentrated in the bright disk, then stars and gas farther out should orbit more slowly, much like planets in the outer solar system move more gently around the Sun. That is not what Andromeda showed. Measurements revealed that gas far from the center was moving faster than expected.
Instead of slowing down, orbital speed stayed roughly constant across much of the disk. This told astronomers that the mass influencing motion extended well beyond the bright regions they could see. The disk was orderly, but it was not telling the whole truth.
Still, the disk itself remained visually neat. Its spiral structure could be traced cleanly. Its thickness and radius were measurable. Compared to the diffuse halo uncovered later, it felt almost architectural. Clean lines, recognizable shape, a galaxy you could draw with confidence. This contrast turned out to be misleading. The disk gave the impression of completeness because human perception prefers structure. Spirals feel intentional. Symmetry feels finished. When light is concentrated into well-defined patterns, the mind assumes boundaries must follow soon after. But a galaxy is not designed to satisfy intuition. The disk is only where conditions are right for stars and gas to gather densely and shine brightly. It is not where gravity stops. It is not where history ends. It is simply where visibility peaks. Beyond the disk, the galaxy becomes quieter. Stars thin out. Gas grows sparse. Structures lose their symmetry. Streams bend and twist. The neatness dissolves into something far more irregular, messy. Even that messiness was invisible for a long time, not because it did not exist, but because it did not glow insistently enough to be noticed. In hindsight, the disk's very clarity worked against it as an indicator of size. Because it was easy to see, it was easy to mistake for the whole. Because its measurements converged early, it felt definitive. And because it behaved predictably in images, it encouraged the idea that Andromeda itself was similarly contained. Rotation measurements quietly contradicted this impression. The motion of gas within the disk hinted that much more mass lay beyond what the eye could trace. The galaxy's gravitational influence reached farther than its bright arms. Something unseen was shaping the disk's motion, holding it together and extending outward into darkness. Yet for years, these implications remained abstract. The disk was still what people pointed to when they spoke of Andromeda's size. It was the part that could be shown, photographed, and compared. The messy outskirts were harder to visualize and even harder to explain. There is a certain comfort in tidy structures. They feel manageable. They invite confidence. Andromeda's disk offered that comfort, even as the data quietly suggested a deeper complexity. Over time, astronomers learned to separate familiarity from completeness. The disk is real, it is important. It contains a vast number of stars and much of the galaxy's visible activity. But it is only one layer, a bright, well-behaved layer sitting inside something much larger and far less orderly. In a sense, the disk is Andromeda's most convincing illusion. It looks like a boundary because it is where light gathers most strongly. It feels like an ending because brightness drops beyond it. But neither impression reflects the true extent of the galaxy. The neatness of the disk made it an excellent starting point. It also made it a poor guide to the galaxy's full scale. Only when astronomers looked past that neatness did Andromeda begin to reveal just how much more there was. At first, the stars appeared where no stars were supposed to be. They showed up quietly at the very limits of deep observations, scattered far beyond Andromeda's bright spiral disk. Individually, they were unremarkable, old, dim, easy to overlook. But taken together, they began to tell a story that reshaped how astronomers understood the galaxy. These stars belong to Andromeda's stellar halo. The halo is not a structure that announces itself. It does not shine brightly or form graceful, swirling patterns like the arms of the disk. It is diffuse, extended, and sparse, made up of stars spread across enormous distances like dust motes caught in a sunbeam. For a long time, it remained hidden simply because it did not glow strongly enough to stand out against the deep black. Deep star counts changed that.
By carefully counting individual stars across wide areas of the sky, astronomers were able to trace Andromeda's population far beyond the visible disk. Red giant stars again played a key role. Their predictable brightness allowed researchers to identify them reliably, even when they were scattered thinly across space. As these surveys expanded, the scale of the halo became impossible to ignore. Halo stars associated with Andromeda were found at distances exceeding 600,000 light-years from the galaxy's center. In some directions, they stretched even farther, dissolving gradually into the surrounding space. This was not a narrow shell or a tidy boundary. It was an enormous, extended envelope of stars surrounding the galaxy like a faint mist. This discovery alone transformed earlier size estimates. If Andromeda's disk had once defined its scale, the halo redefined it entirely. The galaxy was no longer measured only by where its light was brightest, but by where its stars still belonged gravitationally. Including the halo effectively doubled the galaxy's known extent. And this was not speculation. These stars were not random background objects. Their distances, their motions, and their properties matched what would be expected of Andromeda's population. They were part of the system, even if they occupied its quietest, loneliest regions. One of the most revealing clues came from metallicity. In astronomy, metallicity refers to the abundance of elements heavier than hydrogen and helium within a star. Stars formed early in the universe tend to have low metallicity because heavier elements like carbon, oxygen, and iron had not yet been widely produced by generations of stellar evolution. When astronomers measured the metallicity of Andromeda's halo stars, a clear pattern emerged. These stars were old, very old. Many had formed early in the galaxy's history, long before the spiral disk took on its present beautiful form. Some of these stars likely formed within Andromeda itself during its earlier stages. Others were probably acquired later, pulled in from smaller galaxies that wandered too close and were gradually torn apart. Their remains were stretched into long, faint streams that now lace the halo. The halo, it turned out, was a record of Andromeda's past. Every faint star carried information about how the galaxy grew. Each stream marked a merger long completed. Each metallicity measurement added a piece to the timeline. The halo was not just large, it was ancient. It was a museum of the galaxy's childhood. As surveys pushed farther outward, another subtle realization followed. Andromeda's halo does not exist in isolation. The Milky Way has a halo of its own, similarly extended and similarly diffuse. And when astronomers mapped the outskirts of both galaxies, they found that these halos likely overlap. The space between Andromeda and the Milky Way is not empty, it is shared. This overlap does not mean the galaxies are colliding in a dramatic sense, at least not yet. It means their gravitational influence extends so far that their outermost stars occupy the same broad region of space. The boundary between them is not a line, but a transition.
In this shared territory, it becomes difficult to say where one galaxy ends and the other begins. This was a quiet but profound shift in thinking. Galaxies were no longer separate islands surrounded by emptiness. They were expansive systems whose outskirts blended together. Their influence reached far beyond their bright centers, overlapping gently with their neighbors like the edges of two clouds drifting together. Brightness, once again, proved to be a poor guide. The stellar halo is faint precisely because its stars are spread so widely. Their combined light is thin, diluted across vast volumes of space. To the eye, and even to many telescopes, this looks like nothing at all. But the stars are there, moving slowly, bound by gravity, tracing out the true scale of the galaxy. This realization forced astronomers to rethink the idea of an edge. If a galaxy fades gradually rather than stopping, then its edge is not a place, it is a concept. It is a region where membership becomes ambiguous, where stars are few and where definitions grow soft. Andromeda does not end where brightness ends. It continues quietly outward. There was a certain elegance in this conclusion. The most expansive parts of the galaxy are also the least conspicuous. The halo does not dominate images or capture attention. It requires patience, careful measurement, and a willingness to look when nothing obvious appears. Even then, it never fully reveals itself. Its outer limits blur into the larger structure of the local universe. Its stars thin until counting becomes uncertain. Its influence weakens until it blends into the gravitational background shared with other galaxies. This does not make the halo less real. It makes it more honest. The discovery of Andromeda's stellar halo marked a turning point. Size was no longer defined by what could be seen easily. It was defined by what could be traced, inferred, and understood through careful observation. The galaxy that once seemed neatly contained within a spiral disk was now understood as a layered system, bright at the center, diffuse at the edges, vast beyond intuition. And perhaps most importantly, this discovery reframed what it means to belong. A star does not need to shine brightly to be part of a galaxy. It only needs to move with it, to share its gravity, to carry its history. In Andromeda's halo, those quiet stars do exactly that. Once Andromeda's true extent began to come into focus, a new question followed naturally. How many stars does something this large actually contain? It is an inviting question, and also a misleading one. No astronomer has ever sat down to count Andromeda's stars one by one. Even the most powerful telescopes can only resolve a fraction of them, and only in carefully selected regions. The galaxy is simply too vast, too distant, and too densely populated for a direct census. So, astronomers count stars without counting them. The method begins with something that sounds deceptively simple. Instead of asking how many stars there are in total, astronomers ask how many stars of a certain brightness can be seen in a small, representative patch of the galaxy. That patch is chosen carefully, avoiding unusual regions and focusing on areas that reflect typical stellar populations. From there, the work becomes statistical. Stars are not all the same. Some are large and bright, others are small and faint. Most fall somewhere in between. Importantly, faint stars are far more numerous than bright ones, but also much harder to detect. Even with space-based telescopes, many of Andromeda's stars are too dim to be seen individually. This is where luminosity functions come in. A luminosity function is a tool that describes how many stars exist at each brightness level. By measuring how many bright stars are visible and understanding how stellar populations tend to be distributed across brightness, astronomers can infer how many faint stars must be present as well. It is not a guess, it is a structured extrapolation. Astronomers build these functions using well-studied regions where stars can be observed in detail, like our own local neighborhood in the Milky Way. They then apply the same distributions to similar environments elsewhere in the galaxy. By scaling up from small observable regions to the full volume of Andromeda, they can estimate the total number of stars it contains. The result is a number that feels almost unreal. Many studies suggest that Andromeda contains on the order of 1 trillion stars. That is roughly 10 times the commonly cited estimate for the Milky Way, though even that comparison comes with substantial uncertainty. This number tends to attract attention, but it deserves careful handling. 1 trillion is not a precise count. It is an approximation shaped by assumptions about stellar populations, the faintest stars, and how evenly stars are distributed across the galaxy. Change those assumptions, and the number shifts. That variability is not a weakness. It is an honest reflection of the challenge involved. Some estimates arrive at slightly lower totals. Others push higher. The differences depend on how much weight is given to the faintest stars,
how extended the halo is assumed to be, and how stellar density changes with distance from the center. Each of these factors introduces uncertainty.
What matters most is not the exact figure, but the scale it represents. Andromeda is not just slightly more populous than the Milky Way, it operates in a different numerical regime. Hundreds of billions of stars at a minimum, possibly closer to 1 trillion, each one a sun in its own right, with its own history, lifespan, and eventual fate. Even arriving at that range requires careful restraint. Astronomers avoid overconfidence here for good reason. Luminosity functions rely on models of stellar evolution. They depend on assumptions about how many low-mass stars form compared to high-mass ones. They assume that regions not directly observed behave similarly to those that are. These assumptions are well tested, but they are still assumptions. Small changes ripple outward. If faint stars are slightly more common than expected, the total rises. If the halo contains fewer stars than inferred, it falls. The uncertainty grows as the galaxy itself grows. This is why star counts are usually presented as ranges rather than single values. The language is careful. Estimates suggest, data indicate, results are consistent with. There is a quiet discipline to this caution. Comparisons with the Milky Way are handled the same way. Our own galaxy's star count is also uncertain, typically estimated at a few 100 billion stars. Differences in structure, halo size, and star formation history make direct comparison difficult. The Milky Way and Andromeda are similar in some ways and different in others. Neither number is exact, neither needs to be. What matters is perspective. Counting stars without counting them allows astronomers to grasp scale without pretending to control it. It replaces the impossible task of tallying every star with a statistical understanding of how stellar populations behave. It trades precision for realism. There is also something quietly humbling in this approach. Even with modern instruments, Andromeda's stars resist full enumeration. The galaxy remains too large, too distant, and too subtle to be fully captured in numbers alone. Yet the estimates are still powerful. To say that Andromeda contains on the order of 1 trillion stars is not to boast, it is to acknowledge that the galaxy is an environment on a scale that stretches human intuition. The number is not meant to be visualized all at once, it is meant to recalibrate expectation. Each star contributes a small amount of light. Together, they build the glow of the galaxy. Spread across a vast volume, their individual brightness fades, but their collective presence remains. That is why luminosity functions work. They respect the fact that most of the galaxy's content is faint, quiet, and easily overlooked. They allow astronomers to account for what cannot be seen directly by understanding patterns in what can be. There is also a gentle irony here. The most numerous stars in Andromeda are the least conspicuous. Small, long-lived stars, red dwarfs, capture the population, even though they contribute little to the galaxy's visual splendor. Bright stars capture attention, but they are rare. The galaxy's true weight lies in its quiet majority. Seen this way, star counts become less about numbers and more about structure, about how stars form, how they are distributed, how their collective behavior shapes what a galaxy becomes. Andromeda's immense star count does not make it special in a competitive sense, it makes it representative of what large spiral galaxies can be. It is a reminder that scale in the universe often hides behind subtlety. The galaxy looks calm, its light is gentle, but beneath that softness lies a population so vast that it can only be approached statistically. Counting stars without counting them is not a compromise, it is the only way to meet a galaxy on its own terms. Inside Andromeda, this approach began with stars and gas. Astronomers tracked how quickly material orbited the galaxy's center at different distances. These measurements had already hinted that the visible disk did not contain all the mass influencing motion.
Orbital speed stayed high even where starlight thinned. But the most striking clues came from much farther out. Andromeda is surrounded by smaller satellite galaxies, each bound loosely by gravity. These companions move slowly, tracing wide, elongated paths through space. By measuring their velocities and trajectories, astronomers could estimate how much mass Andromeda must contain to keep these satellites from drifting away. The answer was unsettling. The visible stars accounted for only a fraction of the required mass. Even when the disk and stellar halo were included, there was still far too little matter to explain the observed motions. Something else was contributing, something extended, something invisible. This realization did not arrive all at once. It emerged gradually as more satellite galaxies were identified and their motions measured more precisely. Each new data point reinforced the same conclusion. Andromeda's gravitational influence reached far beyond the regions where stars could be counted. Velocity dispersion studies added another layer. Instead of tracking orderly rotation, these studies examined how stars and satellites move in many directions at once. The spread of their velocities, how much they differ from one another, carries information about the depth of the gravitational well they occupy. A shallow well produces gentle motion. A deep one allows faster, more varied movement. Measurements of velocity dispersion around Andromeda pointed to a massive, extended structure enveloping the galaxy. Once again, the mass implied by motion far exceeded what could be seen. This is where size began to mean something new. If mass extends farther than light, then the galaxy's effective size cannot be defined by brightness alone. Gravity does not stop where stars become faint. It weakens gradually, reaching outward into space, shaping the paths of objects that may never shine brightly enough to be noticed directly. In this sense, Andromeda's size is not just about where stars are located, it is about how far its gravity matters. That reach is enormous. Mass estimates derived from stellar motion and satellite dynamics suggest that Andromeda's gravitational influence spans well over 1 million light-years in radius. Some estimates extended farther still. These figures depend on assumptions and methods, but they agree on one point. The galaxy's true footprint is vastly larger than its visible form. This does not mean that stars fill this entire region. Most of it is empty, quiet, and dark. But it is not uninfluenced. Objects moving through this space feel Andromeda's pull. Their paths curve gently. Their velocities reflect the presence of mass distributed across an enormous volume. There is a subtle shift in perspective here. Earlier discussions of size asked where the galaxy ends visually. Mass-based approaches ask where its influence becomes negligible. These are very different questions, and they yield very different answers. It also explains why earlier size estimates felt incomplete. They were focused on what could be seen easily, not on what could be inferred reliably. Light is compelling, but gravity is honest. This reframing helps resolve an apparent contradiction. How could Andromeda's disk look so tidy while its influence stretches so far? The answer is that disks form where matter settles into orderly motion. Halos, by contrast, are shaped by long histories of interaction, merger, and slow accretion. They are sprawling and diffuse, and their mass dominates the outer regions. From the inside, the galaxy feels structured. From the outside, it feels expansive. There is also a gentle lesson in restraint here. Mass estimates are powerful, but they are not exact. Different methods produce slightly different results. Satellite motions sample certain regions more than others. Velocity dispersion depends on assumptions about equilibrium and history. Astronomers know this, they account for it.
Uncertainty is built into the conclusions.
Even so, the overall picture is robust. Andromeda is far more massive than its visible stars alone would suggest. That mass is spread across a vast halo extending well beyond the luminous disk and stellar halo traced by light. This has practical consequences. When thinking about Andromeda's interaction with its surroundings, mass matters more than brightness. Its gravity shapes the motion of nearby galaxies. It influences the structure of the local group. It determines how matter flows on scales far larger than the visible galaxy itself. Size, in this context, becomes relational. It is not about drawing a line around what can be seen. It is about understanding how far influence extends, how far orbits are shaped, how wide the gravitational conversation reaches. We are now drifting deeper into the invisible structure of the galaxy, dark matter, and beginning the gentle comparison with our own Milky Way. There is even a touch of quiet humor in this shift. After decades of refining images, extending exposure times, and counting ever fainter stars, astronomers realized that the most expansive part of Andromeda does not glow at all. The galaxy's greatest reach is invisible, yet it is felt everywhere around it. This does not diminish the importance of light-based measurements. They reveal structure, history, and composition. But mass-based measurements add depth. They transform size from a surface description into a three-dimensional concept. Andromeda is not just a spiral disk surrounded by faint stars. It is a massive system whose gravity quietly organizes space on scales that defy easy visualization. Seen this way, the galaxy's true size is not something you look at, it is something you move within, and that changes the question entirely. By this point, Andromeda had already grown far beyond its bright spiral disk and even beyond its visible halo of stars. Yet the most expansive part of the galaxy was still missing from view. It had never been seen directly, it had only been felt. Dark matter entered the story not as an exotic idea, but as a practical necessity. Astronomers were not searching for mystery, they were simply trying to make sense of motion. Stars, gas, and satellite galaxies were moving in ways that could not be explained by visible matter alone. Rotation curves provided the first persistent clue. As gas and stars orbit Andromeda's center, their speeds reveal how mass is distributed. Close in, where stars are dense and light is strong, orbital motion behaves roughly as expected. But farther out, where light thins and stars grow sparse, something unusual happens. The orbital speeds do not drop off as they should, they remain high. If only the visible stars and gas were present, those outer regions should move more slowly, drifting lazily like planets in the outer solar system. They do not. This pattern repeats not only in Andromeda, but in spiral galaxies across the universe. The implication is straightforward. There is more mass than meets the eye. Satellite galaxies reinforce this conclusion. These small companions orbit Andromeda at great distances, some hundreds of thousands of light years away. Their motions are slow and wide, tracing long, sleepy paths through space. Measuring their velocities reveal how much mass must lie within their orbits to keep them bound to the galaxy. Again, visible matter falls short. Even after accounting for the bright disk and the extended stellar halo, there is not nearly enough mass to explain the motions we see. Something additional must be present, distributed broadly and smoothly across a vast region. That additional component is what astronomers call dark matter. Dark matter does not emit light, it does not absorb it, it does not glow, sparkle, or cast shadows. Its presence is inferred entirely through gravity, through how stars move,
through how gas rotates, through how satellites remain attached to their host galaxies. In Andromeda, the dark matter halo dominates the galaxy's mass. This halo is not a thin shell or a compact structure. It is an enormous, roughly spherical distribution extending far beyond the visible galaxy. Estimates suggest that Andromeda's dark matter halo likely reaches out over 2 million light-years in diameter, perhaps even more.
This means that the galaxy's gravitational influence stretches far beyond where any stars can be seen or even reliably counted. Importantly, this figure is not pulled from thin air. Astronomers combine observations with simulations to understand how such halos behave. Computer models are built using the known laws of gravity and the observed distribution of matter. These simulations are then tested against real data: satellite galaxy motions, velocity dispersions, the overall structure of the local group. When the simulated halos are too small, the satellite motions do not match reality. When they are too massive or too compact, the patterns diverge. Only certain configurations reproduce what is actually observed around Andromeda. Those configurations consistently point to a very large dark matter halo. This process is iterative and careful. Simulations are adjusted, assumptions are tested, results are compared across multiple datasets. There is no single definitive model, but there is a growing consensus about the scale involved, and that scale is vast. At these distances, something else becomes apparent. Andromeda's dark matter halo does not exist in isolation. The Milky Way has a dark matter halo of its own, similarly extended and similarly dominant. When astronomers map the likely extents of both halos, they find that they already overlap. Long before any visible interaction occurs, the invisible structures surrounding the galaxies are intertwined. This overlap does not mean the galaxies are colliding in a dramatic sense. It means that their gravitational environments are shared. The space between them is shaped by both. Objects moving through this region feel the combined influence of two massive systems. In this context, the idea of a clear boundary becomes increasingly difficult to defend. Where does Andromeda end if its dark matter halo blends smoothly into that of the Milky Way? Where does one gravitational domain give way to another? The answer is not sharp, it is gradual. This uncertainty is not a flaw in the science, it is a reflection of how gravity works on large scales. Dark matter halos are not rigid containers, they are diffuse, overlapping, and dynamic. Their edges are defined not by walls, but by declining influence, by regions where gravity weakens enough that other structures begin to dominate. Astronomers are careful here. They do not claim exact sizes with false precision. Estimates of halo extent depend on assumptions about how dark matter is distributed, how satellites have evolved, and how the local group formed over time. Different models produce slightly different answers. Some halos are more extended, others are more compact, but all agree on the central point. The majority of Andromeda's mass lies far outside its visible form. This realization reframes everything that came before. The spiral disk is once again just a bright island inside a much larger sea. The stellar halo, impressive in its own right, is still only a tracer of something more expansive. The true scale of Andromeda is written in gravity, not light. There is also a quiet restraint in how astronomers discuss this. Dark matter is not invoked to create wonder, it is invoked to restore consistency. Without it, the observed motions do not make sense. With it, they do. The concept persists because it works, not because it is dramatic. And yet its implications are profound. If Andromeda's dark matter halo extends over 2 million light-years, then the galaxy's effective size is measured not in where stars fade, but in where gravitational influence becomes negligible. That reach is enormous. It reshapes the structure of the local group. It influences how galaxies move, interact, and evolve. In this light, Andromeda is less an object and more an environment, a region of space organized by gravity, a vast invisible architecture within which stars, gas, and smaller galaxies move.
Its brightest features are merely the most visible expressions of a much deeper structure. There's something quietly humbling about this conclusion. The largest part of the galaxy cannot be seen, it cannot be photographed, it cannot be admired directly. It must be inferred patiently through motion and careful modeling, and even then, it remains partially uncertain. Astronomers know the halo is there. They know it is large. They know it dominates the mass. What they continue to refine is its exact shape, its precise extent, and how it interacts with its surroundings. That uncertainty is not a gap waiting to be sensationalized. It is the normal edge of knowledge, a place where evidence narrows possibilities without eliminating them entirely. Andromeda's dark matter halo reminds us that size in astronomy is often hidden. The most expansive structures are the least visible. The greatest influences leave no light behind. The galaxy does not end where brightness ends. It does not even end where stars end. It fades into gravity.
For many years, Andromeda was described as the larger sibling, the bigger spiral, the more massive neighbor. That comparison felt intuitive. Early measurements suggested Andromeda contained more stars, extended further, and exerted a stronger gravitational pull than the Milky Way. The numbers seemed to support the story, and the idea settled comfortably into textbooks and popular explanations. But comparisons are only as good as the methods behind them. As astronomers refined their techniques, they began to realize that earlier contrasts between Andromeda and the Milky Way were not always made on equal footing. Different assumptions, different data sets, different ways of defining size. When those differences were accounted for, the gap between the two galaxies began to narrow. The first step toward a fair comparison was methodological consistency. When the same tools are applied to both galaxies, the results look more balanced. Disk sizes measured in the same way turn out to be broadly similar. Halo extents, traced using the same stellar populations, overlap in scale. Mass estimates derived from comparable satellite motions converge more closely than once thought. This does not mean the galaxies are identical, they are not, but it does mean that earlier claims of dramatic difference were often overstated. Take visible disks, for example. When astronomers compare the bright spiral disks using similar imaging depth and criteria, Andromeda's disk is somewhat larger, but not by an overwhelming margin. Both galaxies have extended spiral structures, dust lanes, and star-forming regions that taper gradually rather than ending sharply. Once measured consistently, their disks occupy comparable ranges. The same pattern appears with stellar halos. When red giant stars are used as tracers for both galaxies, the halos extend to similar distances. Each galaxy possesses a vast, diffuse envelope of ancient stars, stretching hundreds of thousands of light years from the center. Differences remain, but they are subtle rather than dramatic. Earlier impressions of Andromeda's dominance often came from comparing its halo to an undersampled view of the Milky Way's. From inside our own galaxy, mapping the halo is more challenging. Dust obscures some regions. Perspective complicates distance measurements. We are trying to draw the house while sitting in the living room. As surveys improved, the Milky Way's halo grew outward in much the same way Andromeda's had. Once both were measured with comparable care, the contrast softened. Mass estimates followed a similar path. Early studies often assigned Andromeda a significantly higher mass based on limited satellite data and simplified models. As more satellite galaxies were discovered around both systems, and as velocity measurements became more precise, mass estimates were revised. Recent analyses suggest that the total masses of Andromeda and the Milky Way are closer than once believed. In some models, Andromeda is still revealed to be more massive. In others, the Milky Way takes the lead. In many, the difference falls well within the margin of uncertainty. The important shift is not which galaxy is larger, but how sensitive the answer is to assumptions. How far the dark matter halo extends, how satellites are distributed, how equilibrium is defined. Small changes in these inputs produce different outcomes. Astronomers are well aware of this, and they treat the results accordingly. There is also a psychological factor at play. Andromeda is seen from the outside.
Its structure is visible in a single magnificent frame. Its disk, halo, and satellite system can be surveyed directly. The Milky Way is experienced from within. Its shape must be reconstructed from countless individual measurements. That difference alone makes Andromeda feel larger, even when the underlying scales are similar. Perspective matters. Comparisons become even more nuanced when gravitational influence is considered. Both galaxies possess dark matter halos extending well beyond their visible stars. These halos overlap, sharing a broad region of space. In this context, asking which galaxy is larger becomes less meaningful. Their domains blend. The idea of competition fades quickly at these scales. Neither galaxy exists in isolation. Each has grown through mergers. Each continues to shape the motion of smaller companions. Each participates in the same local environment. Their histories are intertwined even before any future interaction is considered.
Methodology shapes conclusions more than rivalry ever could. When astronomers say Andromeda is larger or that the Milky Way may be comparable, what they are really saying is that different definitions of size highlight different aspects of structure. Diameter emphasizes disks. Halo extent emphasizes ancient stars. Mass emphasizes gravity. Each tells a valid story, but none tells the whole one alone. This awareness has led to a more careful tone in recent work. Claims are framed with uncertainty. Results are presented as ranges rather than absolutes. Comparisons are made using matched samples and shared assumptions wherever possible. The language has softened, not because the science is weaker, but because it is more honest. There is also a subtle shift in emphasis. Instead of asking which galaxy is bigger, astronomers increasingly ask how similar they are. Both are large spiral galaxies. Both possess extensive halos. Both dominate their local environments. Both likely formed through comparable processes, even if the details differ. In that sense, Andromeda and the Milky Way are less rivals and more variations on a theme. There is even a touch of gentle humor in how the comparison has evolved. After decades of arguing over which galaxy holds the title of largest in the local group, the most careful analyses suggest that the answer may simply be that they are much alike, separated more by perspective than by scale. That conclusion does not diminish Andromeda's grandeur, it reframes it. Understanding Andromeda's size helps clarify our understanding of the Milky Way as well. Each measurement informs the other. Each revision sharpens the picture of what large spiral galaxies can be. The real lesson lies in the process. As methods improved, conclusions changed. As data sets expanded, confidence became more measured. As assumptions were aligned, differences narrowed. This is not indecision, it is refinement. Andromeda may still edge ahead in some measurements. The Milky Way may surpass it in others. The exact ranking is less important than the realization that size in astronomy is not a single quantity waiting to be declared. It is a collection of perspectives. Seen this way, comparing Andromeda and the Milky Way becomes less about contrast and more about context. Two galaxies of comparable scale, sharing space, sharing history, and teaching astronomers the same quiet lesson. How you measure determines what you see. Andromeda's influence does not stop with its stars. Long after the bright spiral disk fades from view, and even beyond the faint stellar halo we have just explored, the galaxy continues to shape its surroundings. It does this not through light, which is fleeting, but through gravity, the slow, persistent kind that leaves its mark over immense spans of time. One of the clearer signs of this invisible influence comes from the small galaxies that orbit Andromeda.
These satellite galaxies are scattered across a wide region of space, each moving along a path determined largely by Andromeda's mass. Some are compact and dense, huddled relatively close to the giant. Others are diffuse and fragile, barely holding themselves together against the dark. All of them are bound not by chance but by gravity, acting patiently over billions of years. As astronomers mapped these satellites more completely, a pattern emerged. They were not confined to the immediate vicinity of the bright disk. Many orbited at vast distances, hundreds of thousands of light-years away. Some followed elongated paths, venturing far out into the quiet void before slowly, inevitably curbing back in.
To remain bound on such wide orbits, Andromeda's gravitational reach had to be enormous. Each satellite's motion provides a clue, a whisper of the invisible. By measuring how fast it moves and how far it strays, astronomers can estimate how much mass lies within its orbit. Again and again, the same conclusion appears. Andromeda's influence extends far beyond what its visible stars would suggest. But satellites are not the only evidence. Scattered throughout the space around Andromeda are faint stellar streams. These are long, thin ribbons of stars stretching across the sky, sometimes looping gracefully, sometimes twisting irregularly, like smoke in a still room. These streams are the remnants of smaller galaxies that wandered too close and were slowly pulled apart. They are not violent scars, they are gentle records. As a smaller galaxy falls into Andromeda's gravitational field, tidal forces begin to act. Stars on the near side feel a stronger pull than those on the far side. Over time, this difference stretches the galaxy, peeling stars away layer by layer and spreading them along its orbit. What remains is a stream tracing the path of the encounter. These streams are extraordinarily useful to science. They act like test particles, outlining the shape and strength of Andromeda's gravitational field where we cannot see it. By following their paths, astronomers can infer how mass is distributed throughout the region. Where the stream bends, gravity is guiding it. Where it thins, time has been at work. Some of Andromeda's streams extend hundreds of thousands of light-years. Their very existence shows that the galaxy's influence reaches at least that far, and often farther. A stream cannot persist outside the region where gravity still holds sway. In this way, Andromeda's territory becomes visible, even though it does not shine. This territory is not a fixed boundary like a wall. It is a zone of influence, a region where objects move in response to Andromeda's mass rather than drifting freely through space. Within it, motion is organized. Outside it, other gravitational players begin to matter more. Importantly, all of this happens very slowly. Cosmic motion is unhurried. Satellite galaxies do not whip around Andromeda in short, frantic loops. Their orbits can take billions of years to complete just once. Stellar streams form gradually, stretching over eons as gravity does its work with steady restraint. Nothing here is rushed. This slowness is easy to underestimate. When looking at static images, it is tempting to imagine dramatic events unfolding quickly. In reality, even major changes play out at a pace that makes stillness seem like action. Andromeda's influence grows not through sudden expansion, but through accumulation. Each merger adds mass. Each captured satellite extends the reach of gravity. Each stream marks a chapter in a history written over unimaginable durations. From this perspective, the galaxy's visible body is almost misleadingly small. The bright disk marks where stars are concentrated and active. The stellar halo shows where stars are sparse but still present. Beyond both lies a much larger domain defined not by what can be seen, but by what can be held. This domain includes satellites still intact, streams in the process of dissolving, and debris long since spread thin. All of it responds to Andromeda's gravity. All of it belongs, in a meaningful sense, to the galaxy.
There is also an important subtlety here. Andromeda's territory is not exclusive. In the vastness of space, gravitational domains can overlap. The outer reaches of Andromeda's influence blend with that of the Milky Way and other members of the local group. In these regions, no single galaxy dominates completely. Instead, gravity becomes a shared language. Objects move under the combined influence of multiple masses. Their paths curve gently, shaped by a balance rather than a single pull. The idea of ownership gives way to interaction. Still, within its immediate environment, Andromeda is unmistakably dominant. Its satellites align broadly around it, its streams arc through space in coherent patterns, its mass sets the tempo of motion across a huge volume. Even far from the bright disk, the galaxy's presence is felt. This understanding changes how size is perceived. Asking, how far does Andromeda's influence reach, is different from asking, how large does it look? One question is about appearance, the other is about effect. The first stops where light fades. The second continues until gravity weakens enough to yield control. By that second measure, Andromeda is immense. Its territory encompasses a region far larger than its visible form, a space shaped over billions of years by slow mergers, gentle tides, and steady motion. A domain where stars and galaxies move not randomly, but in quiet response to a massive neighbor. There is a certain elegance in this arrangement. Nothing here announces itself loudly. No sharp borders declare ownership. Influence tapers, control softens, motion slows. The galaxy's reach is revealed only through patience and careful observation. Andromeda does not claim space with brightness, it holds it with gravity. Understanding this reach brings a calmer perspective to cosmic scale. Galaxies are not isolated islands floating in emptiness. They are participants in a shared environment, their influences overlapping and interacting over immense distances. Andromeda's influence reaches far, not because it is aggressive, but because it has existed for a very long time. Given enough time, even a gentle pull can shape an enormous volume. That is the quiet power of a galaxy.
This introduces a quiet complication. When astronomers measure Andromeda's size, they are measuring a historical version of the galaxy. The extent of its disk reflects where stars were distributed in the past. The reach of its halo shows where ancient stars had already wandered by that time. The paths of stellar streams reveal interactions that may no longer be actively unfolding in the same way. Size, in other words, is time-stamped. This becomes especially important when discussing the galaxy's outskirts. The faintest regions, the ones that define its greatest extent, are often the oldest. Halo stars formed early. Streams record events long completed. These structures evolve slowly, but they do evolve. Some stars drift farther out. Some streams stretch and thin. Some satellites lose material over time. The Andromeda that exists at this very second may be slightly more extended, slightly more diffuse than the Andromeda whose light now reaches Earth. Astronomers account for this by turning to simulations using the laws of gravity and well-tested models of cosmic evolution. Researchers simulate how galaxies like Andromeda grow and change over billions of years. These simulations incorporate mergers, star formation, and the slow redistribution of matter. They are not predictions in the everyday sense. They are controlled experiments asking what kinds of histories produce galaxies like the one observed. When simulations are matched to Andromeda's current appearance, they suggest a gentle trajectory of growth. The galaxy is expected to continue expanding its halo gradually as it absorbs small companions and redistributes stars. Its dark matter halo slowly adjusts as mass accumulates. Its visible disk evolves modestly, shaped by ongoing star formation and internal motion. None of this is abrupt, none of it is dramatic. The simulations indicate that Andromeda's overall size changes slowly, measured in tens or hundreds of millions of years rather than in moments. Over the 2 million years represented by the light now arriving, the galaxy would have changed only slightly, enough to matter scientifically, but not enough to invalidate observation. Still, this delay introduces uncertainty. When astronomers say Andromeda's halo extends a certain distance, they are describing where stars were, not where they are now. When they estimate the reach of its gravitational influence, they are working from motions observed in the past. The present-day galaxy exists just beyond direct observation, inferred rather than seen. This does not weaken the conclusions, it clarifies their meaning. Astronomy is always an exercise in patience. The universe does not offer real-time updates. It communicates through delayed signals, and astronomers learn to interpret them with care. Measurements are understood as time averaged, not instantaneous. In fact, this time delay can be an advantage. By observing Andromeda as it was, astronomers gain insight into its history. The structures visible today are the result of long processes already completed. Streams show where mergers occurred. Halo stars reveal early conditions. The galaxy's size encodes its past more clearly than its present. There is also a gentle irony here. The farther out astronomers look, the further back in time they see. The outermost regions of Andromeda are not just spatially distant, they are temporally distant as well. They carry information from earlier stages of the galaxy's evolution. Size and time become intertwined. The larger structures often preserve the older stories. The faint halo stars tell of a formation epoch long gone. The extended streams trace interactions that may no longer be ongoing. The dark matter halo reflects the cumulative history of growth across billions of years. Understanding Andromeda's size, then, is partly an exercise in historical reconstruction. Astronomers compare what is seen to what simulations suggest should exist at different stages of evolution. They adjust models to match observations. They test whether the galaxy's present appearance is consistent with known physical processes. In doing so, they accept uncertainty as part of the picture. No measurement claims to capture Andromeda exactly as it is at this instant. Instead, each describes a version of the galaxy close enough to be meaningful, shaped by a small and well-understood delay. There is something quietly comforting in this limitation. It reminds us that the universe is not rushing. Galaxies evolve slowly. Changes unfold over timescales that dwarf human experience. Even when looking millions of years into the past, the picture remains broadly accurate. Andromeda's size, however defined, is not fleeting. It is stable on timescales far longer than civilizations. The galaxy grows and changes, but it does so with remarkable restraint. This perspective also softens the idea of precision. When astronomers speak of Andromeda's extent, they are not chasing a single exact number. They are describing a range that makes sense given time delays, observational limits, and slow evolution. That range is robust, even if the present-day galaxy differs slightly from what is seen. The light arriving now is old, but it is not misleading. It tells a truthful story about scale, structure, and influence. It just does so with a gentle temporal offset, reminding us that knowledge in astronomy always arrives after the fact.
Seeing Andromeda across time reframes the question of size once more. The galaxy is not a static object waiting to be measured precisely like a box on a shelf. It is a living system, evolving slowly. Its past is continually visible, its present is inferred, and its future is explored through simulation. What we measure is not a moment, it is a history. And in that history, Andromeda has been large for a very long time. For anyone following the story of Andromeda over the decades, one detail can feel oddly unsettled. The numbers keep changing. Its size is revised, its mass is updated, its extent stretches, then steadies, then stretches again. At first glance, this can feel uncomfortable. Surely a galaxy either has a certain size or it does not. But in astronomy, changing numbers are not a sign of confusion. They are a sign that measurement is becoming more precise. Size estimates change because the data improve. It is like a map becoming more detailed. The coastline doesn't move, but our drawing of it becomes truer. For much of the 20th century, astronomers worked with limited information. Distances were uncertain, motions were difficult to measure. Many conclusions rested on indirect indicators and careful inference. These methods were not careless or crude, they were simply the best tools available at the time. As instruments improved, those tools became sharper. One of the most significant advances came from missions designed to measure positions and motions of stars with extraordinary accuracy. By tracking how stars shift against the distant background as Earth moves around the Sun, astronomers can determine distances directly. They can also measure how stars move through space, not just along the line of sight, but sideways as well. This is where missions like Gaia changed the landscape. Gaia mapped the positions, distances, and motions of more than 1 billion stars in the Milky Way and beyond. For Andromeda, its contribution was subtle but profound. While Gaia cannot measure individual distances to most Andromeda stars directly with the same precision as nearby stars, it dramatically improved the calibration of distance indicators and the understanding of stellar motion in the local group. Better distances ripple outward into better size estimates. When the distance to Andromeda is refined even slightly, every measurement tied to that distance adjusts. The physical size of the disk changes, the scale of the halo shifts, the inferred mass distribution responds accordingly. What once seemed like a small revision can reshape multiple conclusions at once. We are continuing the discussion on why scientific numbers change and then shifting perspective to what it would actually feel like to float inside the galaxy, a section focused on vastness and calm.
This is not correction in the everyday sense. It is refinement. Earlier astronomers were not wrong to work with the numbers they had. Their estimates were constrained by the data available. As new information arrives, conclusions are updated to reflect a clearer picture. The earlier work remains valid within its original limits. This process is visible throughout Andromeda's story. Early measurements focused on the bright disk because that was what could be seen. Later observations revealed the halo. Still later, improved motion data reshaped mass estimates. Each stage added depth rather than overturning what came before. Think of it like adjusting the focus on a camera lens. The object does not change, the clarity does. Better data also reduce uncertainty in subtle ways. Instead of producing a single number, astronomers often narrow the range within which that number likely falls. A disk size might not be revised dramatically, but confidence in that size increases. A mass estimate may shift slightly, but the error bars shrink over time. The picture becomes more stable even if individual values continue to evolve. Motion measurements play a particularly important role here. As astronomers gain more precise information about how stars and satellite galaxies move, they can infer mass distributions more accurately. Small errors in velocity can lead to large differences in mass estimates, especially at great distances. Improving those measurements reshapes the inferred gravitational structure. This is why size and mass estimates are often revised together. They are linked through motion. There is also an important cultural aspect within astronomy that shapes how these changes are handled. Scientists are cautious by design. New results are compared against existing ones. Discrepancies are examined rather than celebrated.
When a new estimate differs from an older one, the question is not which is right, but why do they differ? Is the data set larger? Is the method improved? Are the assumptions more realistic? Only after this careful comparison do conclusions shift. This approach prevents dramatic swings based on limited evidence. It ensures that revisions are incremental, grounded, and well understood. When Andromeda's size estimates change, they do so gradually, guided by accumulating evidence rather than sudden reinterpretation. There is also a reassuring pattern to these revisions. Each improvement in measurement tends to add complexity rather than remove it. Andromeda has not become simpler with time, it has become more layered, more extended, more nuanced. That consistency suggests the underlying picture is converging, even if the details continue to sharpen. Changing numbers in this context are not moving targets, they are tightening estimates. It is worth remembering that astronomy deals with extraordinary scales. Small percentage changes can correspond to hundreds of thousands of light years. What looks like a large revision on paper may represent a modest adjustment relative to the galaxy's full extent. This can make progress feel noisy when it is in fact steady. There is also a human element to all of this. Astronomers are careful not to overstate certainty. When new data arrive, they resist the urge to declare final answers. Instead, they integrate the information, update models, and communicate results with appropriate restraint. This can give the impression that the science is unsettled, when in reality it is becoming more robust. Andromeda's size has not been bouncing randomly over time. It has been expanding in understanding as new components are revealed and old assumptions refined. Each revision has moved the picture closer to reality, even if that reality remains complex. There is a quiet maturity in this process. Science does not advance by erasing the past, it advances by building on it. Earlier work provided the foundation that made later discoveries possible. Without initial disk measurements, there would be no baseline for halo expansion. Without early mass estimates, there would be no context for dark matter halos. Every stage depends on the ones before.
This perspective reframes changing numbers as a success story. They show that instruments are improving, that methods are becoming more consistent, that models are being tested against richer data sets. They also show restraint. Astronomers do not rush to simplify a galaxy that is inherently complex. They accept that some uncertainty will remain, especially at the larger scales. They refine what can be refined and leave open what cannot yet be settled. In the case of Andromeda, this means size estimates will likely continue to adjust, but within narrowing bounds. The disk is well characterized. The stellar halo is mapped with increasing confidence. The dark matter halo is constrained by growing data sets and improved simulations. The broad picture is stable, even as the details sharpen. There is even something quietly encouraging in watching the numbers change. Each update represents another step toward understanding something unimaginably large, distant, and subtle. It is evidence that the tools are working. Changing estimates do not mean astronomers are unsure what Andromeda is. They mean astronomers are learning how to describe it more accurately, and that learning is ongoing. In astronomy, certainty is not a fixed point. It is a direction, and with each refinement, the view becomes clearer, calmer, and more complete. Now, let's shift our perspective entirely. Instead of looking at Andromeda from the outside, imagine being inside it. Imagine drifting through the space between its stars. Despite how it is often depicted in art and movies, the galaxy would not feel crowded. There would be no glowing traffic of stars passing close by, no dense walls of light pressing in from every direction. In fact, the most striking feature would be space, vast, quiet space. Astronomers know this because star density inside Andromeda has been measured carefully. By counting stars in small regions and scaling outward, it becomes clear that even within the bright spiral disk, stars are separated by enormous distances. Typical spacing between stars is measured in light years, not in fractions of a year, not in months, but in the distance light travels over multiple years. That spacing remains surprisingly consistent. Even in the denser parts of the disk, stars are usually several light years apart.
In the spiral arms, where stars are somewhat more concentrated, the distances shrink slightly, but not enough to feel enclosed. You could travel for years at the speed of light and still pass nothing but darkness between one star and the next. This alone dissolves one of the most common myths about galaxies. They look dense because their light is compressed into an image. Millions or billions of stars are projected onto a flat surface, stacked visually on top of one another. But depth is lost in that compression. In reality, those stars are scattered through three-dimensional space, separated by distances so large that the galaxy feels more like a fog than a crowd. If you were inside Andromeda, most directions would appear dark. Stars would be points of light rather than walls of glow. The sky would be filled with pinpricks, not floods. Even near the central regions where star density increases, the feeling would remain open and spacious. Measurements of stellar density confirm this calm arrangement. Astronomers estimate the number of stars per cubic light-year in different regions of the galaxy. Even in Andromeda's core, where stars are more tightly packed, the average separation is still measured in tenths of a light-year, not in astronomical closeness. Outside the core, distances grow rapidly. In the spiral disk, the environment would feel broadly similar to the neighborhood of our own sun. Wide gaps, long silences, occasional brilliance surrounded by darkness.
Moving outward into the stellar halo, the sense of space becomes even more pronounced. Halo stars are sparse by design. They occupy a vast volume with enormous distances between them. You could drift for tens or hundreds of light years without encountering another star. This sparsity is not emptiness, it is structure at a different scale. The halo exists not because stars are numerous there, but because gravity holds them together across long distances. Their presence is subtle, but meaningful. Each star traces the galaxy's mass, even when it contributes little light. From within, Andromeda would not announce its size through density, it would do so through extent. No matter which direction you looked, there would always be more space beyond the next star. The galaxy would feel boundless, not because it is filled, but because it is spread out. There is also a quiet regularity to this arrangement. Stars orbit the galaxy's center on long, slow paths. Their motions are gentle. Collisions between stars are extraordinarily rare. In most regions, they are effectively impossible over the lifetime of the universe. The galaxy is dynamic, but not chaotic. This is another myth worth setting aside. Galaxies are not turbulent swarms. They are slow systems governed by gravity, acting patiently. Inside Andromeda, change happens gradually. Orbits evolve over hundreds of millions of years. Structures shift over billions. If you were to remain in one place for a human lifetime, almost nothing would appear to move at all. Even the densest star clusters within Andromeda offer more space than intuition expects. Globular clusters pack stars closer together than the surrounding disk, but even there, the distances are vast compared to everyday experience. These clusters are exceptions, not the rule. Most of the galaxy is quiet. The second-person perspective helps clarify this. You would not feel surrounded, you would feel suspended, embedded within a structure defined more by absence than presence. Light would arrive from all directions, but gently diluted by distance. The galaxy's immense star count does not translate into congestion. 1 trillion stars spread across such a large volume produce a remarkably sparse environment. Scale does the work. This spaciousness is essential to how galaxies function. If stars were packed closely together, gravitational interactions would disrupt orbits and destabilize systems. The calm spacing allows galaxies to persist for billions of years without tearing themselves apart. Stability emerges from distance.
There is even something quietly reassuring in this. Despite its immense size, Andromeda is not overwhelming from the inside. It does not press in. It does not crowd. It offers room to exist.
Visualizing this correctly requires letting go of familiar imagery. No swirling tunnels of light, no dense clouds of stars brushing past. Instead, a wide-open expanse punctuated by occasional brilliance. Star density data supports this image at every scale. As you move from the core to the disk, from the disk to the halo, the trend is always the same. Density falls, space increases. The galaxy fades rather than fills. This fading does not diminish Andromeda's presence, it defines it. Inside the galaxy, size is felt not through pressure, but through patience, through the knowledge that even after traveling immense distances, you would still be within its gravitational embrace. The calmness of this environment stands in contrast to how galaxies are often imagined. Andromeda is not a place of constant motion and collision. It is a place of long orbits, gentle tides, and quiet persistence. Seen from within, the galaxy's true character becomes clear. It is large, not because it is crowded, but because it is extended. It is impressive, not because it is loud, but because it is spacious. And within that space, there is room enough for time to pass slowly.
This realization reframes the question of size once again. Andromeda feels enormous not because it is unique, but because spiral galaxies themselves are enormous. The Milky Way shares this scale. So do many others scattered throughout the universe. What feels extraordinary is not Andromeda specifically, but the category it belongs to. There is also an important selection effect at work. Large galaxies are easier to study. They are brighter, their structures are more pronounced, their halos are more readily traced. Smaller galaxies, especially faint ones, are harder to detect and characterize. This can skew intuition, making large spirals feel more common or more significant than they are. When astronomers account for this bias, the picture becomes clearer. Most galaxies in the universe are actually smaller than Andromeda. Dwarf galaxies are far more numerous. They contain fewer stars, extend over shorter distances, and exert more limited gravitational influence. Against this backdrop, Andromeda stands out as a heavyweight, but not as an anomaly. It is simply a mature spiral in a universe that produces many such systems. Comparisons also highlight how definitions shape perception. If size is defined by visible disk diameter, Andromeda ranks high but not at the top. If size is defined by stellar halo extent, it again appears large but still within expected bounds. If size is defined by dark matter halo reach, the uncertainty grows, but Andromeda remains consistent with other galaxies of similar mass. Each definition places it in a slightly different position within the distribution, but none isolated as extreme. This reinforces an important idea. There is no single ranking that captures what it means for a galaxy to be big. Different measures emphasize different aspects of structure. When those measures are applied consistently, Andromeda behaves exactly as it should. There is a quiet comfort in this consistency. The galaxy that once seemed to stretch endlessly outward turns out to be a well-behaved member of a larger population. Its vastness does not require special explanation. It emerges naturally from the same processes that shape countless other spirals: growth through merger, accumulation of dark matter, long-lived star formation. These are common mechanisms. Andromeda simply represents their outcome on a generous scale.
Even its environment reflects this normalcy. Andromeda resides in a modest group of galaxies, not a dense, chaotic cluster. This has allowed it to grow without frequent disruptive encounters that might have stripped it bare.
Many large spirals in similar quiet environments show comparable sizes and structures. The absence of extreme crowding has preserved its disk and allowed its halo to expand gently over time. Again, nothing unusual is required to explain why it looks the way it does. This perspective also tempers earlier narratives that framed Andromeda as a dominant giant. It is dominant locally, yes, but cosmically it is one of many. Its size is impressive, but not singular. Its influence is strong, but not unrivaled. Understanding this does not diminish Andromeda, it places it properly. Relational scale is the key. A galaxy's size means little in isolation. It gains meaning only through comparison. Against smaller dwarf galaxies, Andromeda is enormous, a titan holding court. Against the largest known spirals in the universe, it is moderate. Within the broad family of mature spirals, it feels at home. This relational view also helps resolve lingering questions about measurement. When size estimates change slightly, Andromeda does not jump wildly within the distribution. It shifts gently, remaining within the same general range. That stability suggests our underlying understanding is sound, even as the details are refined. There is also a subtle lesson here about perspective. From Earth, Andromeda feels special because it is close. It dominates the night sky in a way distant galaxies do not. That proximity makes its scale easier to sense and harder to contextualize. When placed among thousands of others, its familiarity becomes an asset rather than a distortion. It serves as a reference point. Astronomers often use Andromeda as a benchmark when studying spiral galaxies further away. Its size, mass, and structure provide a concrete example against which others can be compared. In this role, its normalcy is precisely what makes it valuable. A galaxy that behaved oddly would be less useful as a standard. So, Andromeda's size, when viewed broadly, tells a reassuring story. It confirms that the processes shaping galaxies operate consistently across the universe. It shows that large spirals are not rare accidents, but natural outcomes of cosmic evolution. The galaxy does not stand apart from the universe, it fits within it. Seen this way, Andromeda's vastness feels less like an exception and more like a pattern, one instance of a common theme expressed on a grand scale. It is large, yes, but it is large in the way many galaxies are, and that makes its size not just impressive, but understandable. But size is not just a measure of the present, it is also a trajectory. The future size of Andromeda is not something that will arrive suddenly. It will unfold slowly, almost imperceptibly over spans of time that resist everyday intuition. Astronomers explore this future using simulations, not predictions in the sense of forecasting tomorrow's weather, but careful reconstructions of how galaxies evolve when gravity is allowed to act over billions of years without interruption. These simulations begin with what is known today: the distribution of stars, the extent of dark matter, the motions of satellites. From there, the clock is allowed to run forward. What emerges is not a story of abrupt change, but of steady, breathing growth. Galaxies like Andromeda increase in size primarily through mergers. Small galaxies drift nearby, become gravitationally bound, and are slowly absorbed into the larger structure. This process is neither violent nor fast. A merger can take billions of years from beginning to end, with most of that time spent in gradual adjustment rather than disruption. The first components to interact are not the bright disks, they are the halos. Dark matter halos extend far beyond visible stars, and they are the first regions to overlap when galaxies approach one another. Long before stars respond, the invisible structures begin to merge, blending smoothly and redistributing mass across a larger volume. This happens quietly. As halos merge, the combined gravitational field becomes more extensive. The effective size of the system grows, even if nothing dramatic appears to be happening to the stars themselves. Stars continue their orbits, disks remain intact. The change is real, but subtle. Simulations consistently show this pattern. Halo growth leads, visible structure follows later, if at all. For Andromeda, this means that its future size will likely increase gradually as it continues to absorb smaller companions. Each merger adds stars to the outskirts, extending the stellar halo further into the dark. Each addition slightly reshapes the dark matter distribution, increasing the gravitational reach. None of this resembles a collision in the everyday sense. There are no sudden impacts, no sharp boundaries crossing. Instead, there is a long period of mutual influence, stretching and redistributing material with gentle persistence. Even when galaxies eventually share visible stars, the process is drawn out and calm. Time does the work. Simulations suggest that Andromeda's halo will continue to grow for billions of years, becoming more extended and more diffuse. Its visible disk may change only modestly, maintaining its general structure while slowly evolving internally. The most dramatic changes remain confined to the faint outskirts. This reinforces a theme that has appeared repeatedly in our story. The parts of a galaxy that grow the most are often the parts that shine the least. It is also worth noting how slow this growth truly is. On the scale of human history, nothing noticeable will happen. On the scale of civilizations, the galaxy will appear unchanged. Even on the scale of millions of years, the differences will be subtle. Only when measured across billions of years does the accumulation become clear. This slowness is not a limitation, it is a feature. Galaxies persist because change is gradual. Their structures are not fragile, they are resilient, shaped by long-term balance rather than short-term disturbance. Andromeda's future size reflects this stability. There is sometimes a temptation to frame the future of Andromeda in dramatic terms, to imagine sudden encounters or decisive moments. But the reality, as revealed by simulations, is quieter. Growth is continuous, boundaries soften, influence spreads, halos blend long before disks respond. By the time visible structures interact, the gravitational relationship has already been established for a very long time. The system has been evolving as one for ages. This perspective changes how the future is understood. Andromeda is not heading toward a single defining event that will suddenly make it larger. It is already becoming larger, slowly, through processes that began long ago and will continue far into the future. The galaxy's size, then, is not a static property waiting to be updated. It is a living trajectory. Each merger adds a layer. Each redistribution extends the reach. Each passing billion years smooths the structure further. Even simulations that explore far futures show this same restraint. The overall shape evolves, but the system remains recognizable. The galaxy does not explode into chaos, it adapts. There is even a certain quiet humor in this. After all the effort to measure Andromeda's size precisely, the future suggests that the answer will never stop changing. Not because the measurements are flawed, but because the galaxy itself is still in the process of becoming. This does not make the present understanding obsolete. It places it in context. Astronomers measure Andromeda's size as it is now, knowing that now is just part of a continuum. The values are meaningful snapshots, not final statements. They capture a stage in a long, slow evolution. The future size of Andromeda will be larger than today's estimates suggest, but it will arrive gently, layered atop what already exists. No sudden transformation will announce it. In the end, Andromeda's growth is not about expansion into emptiness. It is about incorporation, drawing in what is already nearby, sharing gravitational influence, becoming more extended through patience rather than force. Measured in billions of years, the galaxy will grow. Measured in moments, it will appear still. That contrast is at the heart of galactic evolution. Andromeda's future size is not something to wait for, it is something already underway.
By the time Andromeda has been examined from every angle, one quiet realization settles in. Size, in astronomy,
is not a single thing. It is not a number waiting to be discovered and written down in a book. It is not a boundary that can be drawn with confidence and left unchanged. Instead, size depends on what is being asked, how it is measured, and which aspect of a system is being considered. Andromeda taught astronomers this lesson slowly. At first, size meant brightness, how wide the glowing disk appeared against the night sky, how far spiral arms could be traced before they faded into darkness. This was a natural starting point. Light is what telescopes see most easily. It offers structure, contrast, and shape. But brightness turned out to be a guide, not a definition. As observations deepened, size began to include faint stars beyond the disk. Halo stars stretched the galaxy outward, revealing that what appeared complete was only the most visible layer. Size expanded again, not because the galaxy changed, but because understanding did. Then gravity entered the conversation. When astronomers measured motion, size took on a new meaning. The reach of a galaxy could be inferred not by where stars shone, but by how far its mass influenced movement. Satellite galaxies, stellar streams, and velocity patterns all pointed to a much larger domain, one that could not be photographed directly. Here, size meant influence. Andromeda's gravitational reach extended far beyond its visible form, reshaping how astronomers thought about where a galaxy truly ends. The idea of a clean edge began to dissolve. Instead of borders, there were gradients. Instead of lines, there were transitions. Theory added another layer. Simulations showed how galaxies grow over time, how halos merge before disks, how mass redistributes slowly across billions of years. From this perspective, size was no longer a static property. It was a stage in an ongoing process, a moment along a trajectory. Each definition was valid. None was complete on its own. Observational size describes what can be seen. Gravitational size describes what can be felt. Theoretical size describes what emerges over time. Together, they form a fuller picture.
Andromeda sits at the intersection of all three. Its bright disk gives a sense of structure. Its stellar halo reveals history. Its dark matter halo defines influence. Its future growth places all of this within a long continuum. What this teaches is not just something about Andromeda, but something about astronomy itself. Measurements do not converge on a single truth by accident. They do so by context. When astronomers specify how size is defined, their conclusions become clear and consistent. When definitions are mixed, confusion arises. Andromeda was once described as growing larger with every new study. In reality, understanding was growing larger. Each method revealed a different aspect of the same system. There's a gentle humility in this realization. Astronomy deals with objects so vast that no single perspective can capture them fully. Light offers one view, motion offers another, models offer a third. Each reveals something the others cannot. Andromeda, by refusing to fit neatly into one definition of size, helped make this clear. It also softened the idea of precision. Rather than chasing a single definitive measurement, astronomers learned to describe size in terms of ranges, contexts, and relationships. A galaxy can be this wide in light, that extensive in gravity, and larger still in theoretical reach. All of these statements can be true at the same time. This approach does not weaken understanding, it strengthens it. There is also a shift in emotional tone that comes with this broader view. Once size is no longer treated as a fixed answer, the urgency to pin it down fades. What remains is appreciation for scale, structure, and process. Andromeda becomes less of a problem to solve and more of a system to understand. The galaxy is large in ways that matter differently depending on where attention is placed. It is large in star count, large in extent, large in influence, large in history. None of these qualities cancels the others. They layer together. Even uncertainty takes on a different character. Uncertainty is not a gap in knowledge waiting to be closed. It is a measure of how complex the system is. Where boundaries blur, astronomy responds not by forcing clarity, but by refining questions. Andromeda's size remains slightly uncertain at its furthest edges because the galaxy itself does not offer a sharp stopping point. Its influence fades, its stars thin, its gravity blends with that of its surroundings. This is not a failure of measurement, it is a property of galaxies. The lesson extends beyond Andromeda. Every galaxy, when examined closely enough, behaves in the same way. Bright centers give way to faint outskirts. Clear structures dissolve into diffuse halos. Influence stretches farther than light. Size becomes relational rather than absolute. Andromeda simply happened to be close enough, large enough, and well-studied enough to make this lesson unmistakable. There is also something quietly reassuring here. The universe does not demand perfect definitions. It allows for softness at the edges. It permits overlap. It tolerates ambiguity. Understanding deepens not by eliminating this ambiguity, but by learning to work within it. For Andromeda, this means that asking, "How big is it?" will always depend on the lens through which the question is asked. The answer shifts gently with context, not because the galaxy is elusive, but because it is rich. As this realization settles, the question of size begins to feel less urgent. What matters more is what size reveals about formation, about motion, about time, about how matter organizes itself across immense distances. Andromeda is large not just in scale, but in what it teaches. It shows how galaxies are layered systems rather than simple shapes. It demonstrates that influence matters as much as appearance. It reminds astronomers that measurements improve by adding perspectives, not by replacing them. In the end, size in astronomy is not about drawing a line and declaring completion. It is about understanding relationships between stars and space, between light and gravity, between present appearance and long history. Andromeda holds all of these relationships at once. As the focus begins to soften, the galaxy no longer feels like an object to be measured from the outside. It feels like an environment, extended, layered, and patient. Its size is not a single answer. It is a quiet collection of truths. And that understanding carries naturally forward toward reflection rather than resolution, where the need to define gives way to the freedom to observe.
So, how big is the galaxy we call Andromeda? By now, the answer feels less like a single number to be memorized and more like a layered understanding to be felt. We have traveled from the bright, compact center out to the faint, misty edges. We have looked at it through the eyes of early astronomers squinting through brass telescopes and through the digital eyes of spacecraft floating above our atmosphere. We have measured it by its light, by its stars, by its gravity, and by its history. And what we have found is that the galaxy is not just one thing. It is many things, all occupying the same space, all true at the same time. The galaxy has a bright spiral disk. This is the face of Andromeda that is most familiar, the one that smiles back at us from photographs. It can be measured and traced with care. We know its diameter. We know how its arms curve. We can point to it and say, there it is. It feels solid, structured, and manageable. But we also know now that this disk is just the beginning. Wrapping around that disk is a vast halo of ancient stars, extending far beyond the point where our eyes tell us the galaxy should end.
These stars are the quiet sentinels of the galaxy, tracing a sphere of influence that dwarfs the visible spiral. They tell a story of a galaxy that does not stop. It simply thins out. It fades gently into the dark, refusing to draw a sharp line between itself and the rest of the universe. And beyond the stars, there is the even larger gravitational presence, the dark matter halo, the invisible architecture that holds it all together. This dominance is felt by satellite galaxies dancing in slow motion hundreds of thousands of light years away. It is traced by thin streams of stellar debris that loop through the void like ribbons. This version of Andromeda is immense, a giant that shapes the flow of the entire local group, yet it remains completely unseen. And finally, there is the galaxy of time, the Andromeda that is changing, growing, evolving, the one that existed 2 million years ago, whose light is just now touching our retinas, and the one that exists right now, slightly larger, slightly different, hidden behind the delay of light speed. All of these answers are true at once. Andromeda is measurable. Astronomers can estimate its diameter, its mass, its star count, and the reach of its influence. Those measurements are grounded in observation, motion, and careful modeling. They are not guesses. They are the result of decades of patient work, refined again and again as better data becomes available. And yet, Andromeda is also open-ended. Its edges fade rather than stop. Its influence blends into the surrounding space. Its distant components resist sharp definition. This combination of clarity and openness is not a flaw in our understanding. It is what understanding looks like at a cosmic scale. In our everyday lives here on Earth, we are used to things having edges. A table ends where the air begins. A room has walls. A road has a shoulder. We find comfort in these boundaries because they help us organize our world. Uncertainty often feels like a problem to be solved, a gap that needs to be closed. But in astronomy, and particularly when looking at something as grand as a galaxy, uncertainty takes on a different feeling. It is often a sign that the questions being asked are appropriately large. When dealing with galaxies, clean boundaries are rare. Gradients, overlaps, and slow transitions are the rule rather than the exception. Andromeda demonstrates this beautifully. Each attempt to define its size revealed something new, but it never erased what came before. Light showed structure. Faint stars revealed history. Motion uncovered hidden mass. Simulations added time.
The galaxy did not become more confusing as knowledge grew. It became richer. It became more like a living environment and less like a static object. There is something quietly reassuring in this process. It shows that true understanding does not require final, rigid answers. It requires careful framing. When astronomers say how large Andromeda is, they are not claiming to have captured it completely. They are describing the galaxy from a particular perspective with a particular set of tools. That perspective can change. The galaxy remains. This layered reality invites us to relax our grip on the need for precision. We don't need to choose between the bright disk and the faint halo. We don't need to decide if the gravity is more real than the light. We can hold all of it in our minds simultaneously. We can visualize the bright core glowing with the energy of billions of suns. We can extend our imagination outward to the quiet, lonely stars of the halo drifting in the deep silence. We can feel the heavy, invisible pull of the dark matter anchoring the system in the void. And we can see the slow, breathing motion of the whole structure as it drifts through eons of time. It is a complex picture, but it is also a peaceful one. It suggests that everything is connected, that boundaries are softer than we think, and that influence reaches further than we can see. The galaxy is a system where the very large and the very small, the bright and the dark, the past and the present, all dance together in a slow, silent rhythm. There is a specific kind of peace that comes from contemplating this. It is the peace of knowing that some things are simply too big to be contained by a single number. They require a story. They require a shift in how we see. And in that shift, there is a release. We stop trying to measure the galaxy against our human expectations and start appreciating it for what it is, a vast, unfolding phenomenon that has been here long before us and will be here long after us. The layers of Andromeda do not compete with each other. The halo does not hide the disk, it cradles it. The dark matter does not obscure the stars, it holds them. The past does not contradict the present, it creates it. In this way, the galaxy is a perfect model of harmony. Everything has its place, everything plays its part. The massive and the minute work together to create the grand spiral that hangs in our night sky. As we let this layered understanding settle in, the question, how big is it, begins to change. It becomes less of a demand for facts and more of an invitation to wonder. It invites us to step outside of our small, defined world and float for a while in a universe where things are vast, connected, and softly defined. It invites us to rest in the knowledge that we don't need to know exactly where the edge is to know that we are looking at something magnificent.
Andromeda is large enough to hold all these truths. It is large enough to be a disk, a halo, a gravitational well, and a history lesson all at once. It is large enough to be a scientific puzzle and a source of nightly beauty. It is exactly as complex as it needs to be to work, and exactly as simple as it needs to be to admire. So as we drift through these layers, moving from the bright center to the invisible edge, we are not just measuring a galaxy, we are learning how to look at the universe. We are learning that the deeper we look, the more we find, and that every boundary we think we see is just a threshold to something else. The galaxy is not a thing that stops, it is a thing that continues. And in that continuity, there is a profound and gentle silence. A silence that invites us to stop counting, stop measuring, and simply let go. From Earth, Andromeda appears as a calm glow in the night sky. It does not advertise its scale, it does not demand attention. To the unaided eye, under a dark sky far from city lights, it looks like a small, detached piece of the Milky Way that has drifted off on its own. It is a smudge, a thumbprint of light pressed against the black velvet of space. It is quiet, unassuming, and easy to miss if you do not know exactly where to look. Its vastness is subtle, revealed only through patience and perspective. This subtlety is part of its lesson. The universe is full of structures that are larger than our intuition allows, yet gentle in their expression. Size does not always announce itself with brightness or drama. Sometimes, true enormity reveals itself through quiet accumulation, through faint stars counted carefully, through motions traced over long spans of time, through the slow, invisible pull of gravity. Andromeda reminds us that scale in the universe is not about spectacle, it is about context. When we stand in a dark field and look up at that faint oval of light, we are seeing the combined glow of 1 trillion suns. 1 trillion! Yet across the gulf of 2.5 million light years, that roaring nuclear fire is reduced to a whisper. The distance acts as a filter, stripping away the noise, the heat, and the violence of individual stars, leaving only a soft, milky radiance. It turns a galaxy into a ghost. But now, holding all that we have learned in our minds, we can look at that smudge and see more. We can see the invisible. We can imagine the vast halo of stars spreading out like a mist, covering a patch of sky as wide as an outstretched hand, even though our eyes can't register it.
We can feel the immense weight of the dark matter holding the system together, reaching out to touch the edges of our own galaxy. We can sense the slow, majestic rotation, a wheel turning once every few 100 million years. The galaxy is vast, yes, but it is also patient. It is exactly as large as it needs to be. You can let that scale rest where it is. There is nothing more you need to hold on to. The universe is in no hurry, and neither are we. Consider the light that is hitting your eye when you look at Andromeda. That light is old. It is a traveler from a different time. It left the stars of Andromeda before humans had built cities, before we had written languages, before we had even left the cradle of our evolution. It has been traveling in the empty, silent void for all that time, uninterrupted, carrying the image of the galaxy as it once was. And now, tonight, it arrives. It ends its journey on the retina of your eye, or on the sensor of a camera, or in the mirror of a telescope. That connection is intimate. It is a direct line between you and the deep cosmos. And yet, the galaxy it connects you to is so large that it defies comprehension. This duality, the intimacy of the light and the immensity of the source, is one of the most beautiful feelings in astronomy. It makes you feel small, but not insignificant. It makes you feel part of something vast. When we place Andromeda among other galaxies in our mental map, it settles comfortably. It is large, but not extreme. It is dominant locally, but normal cosmically. Seen from within, it would feel spacious rather than crowded. Viewed across time, it is stable, yet slowly evolving. Considered through gravity, it is expansive beyond what light alone can show. All of these views coexist in that faint patch of light. As this understanding settles, the original question softens. How big is Andromeda becomes less of a demand for a hard fact and more of an invitation to perspective. It invites us to widen our view. It invites us to look at the night sky not as a flat dome painted with lights, but as a deep three-dimensional ocean where islands of stars drift in the dark. The galaxy is large in the ways that matter for stars, for motion, for history, and for time, and it has been so for a very long while. There is no need to rush toward a final definition. The universe does not require one. It allows size to remain relational, layered, and gently uncertain. That uncertainty is not a gap waiting to be closed. It is space. Space for refinement, space for discovery, space for calm reflection.
Think about the astronomers who have spent their lives studying this object. They have watched it change from a nebula to a galaxy, from a disk to a halo, from a visible object to a dark matter giant. They have seen the numbers shift and settle. They have watched the boundaries dissolve. And through it all, the galaxy has remained the same peaceful presence in the sky. Our understanding changes. The galaxy endures. There's a lesson in that endurance. Andromeda is not striving to be big. It is not trying to expand or conquer. It simply is. It follows the laws of physics, gathering mass where gravity dictates, forming stars where gas compresses, fading out where the fuel runs low. It is a natural process, playing out on a scale that makes our daily worries seem vanishingly small. When you look at Andromeda, you are looking at gravity's masterpiece. You are seeing what happens when matter is left alone for billions of years to organize itself. It settles into a spiral. It builds a core. It surrounds itself with a halo. It balances itself perfectly against the pull of the void. It is a structure of immense elegance, built without blueprints, maintained without effort. And deep within that structure, on the scale of individual worlds, who knows what quiet stories are unfolding? With 1 trillion stars, the possibilities are endless. There could be planets with skies full of double suns. There could be worlds drifting in the quiet outer halo, seeing the galaxy only as a distant bright band in their night. There could be civilizations looking back at us, seeing the Milky Way as a faint smudge in their own sky,
wondering if anyone is looking back. We don't know. The distance keeps those secrets. But the size of the galaxy ensures that the possibilities are vast. Space is the canvas for possibility. The larger the galaxy, the more room there is for the universe to try different things, to experiment with different forms of worlds, different arrangements of light and shadow. But tonight, we don't need to worry about the details. We don't need to catalog the planets or map the stars. We only need to feel the scale. We need to let the idea of 200,000 light years wash over us like a slow wave. We need to let the weight of 1,000,000,000,000 suns settle gently in our minds. We need to let the silence of the dark matter halo quiet our thoughts. Imagine the galaxy breathing, not a fast breath, but a breath that takes an eon. Inhale, gas falls into the disk, fueling new stars. Exhale, winds from those stars push material back out. Inhale, a small satellite galaxy is drawn in. Exhale, a stream of stars is stretched out into the halo. It is a slow, rhythmic cycle of growth and recycling that has been going on for 10 billion years. We're just catching a single frame of that movie, a single heartbeat in the life of a giant. And that frame is frozen for us by the vast distances involved. It looks still, but it is alive with the slow motion of the cosmos. As we near the end of our journey, let's take a moment to appreciate the darkness. Without the dark, we would not see the galaxy. The contrast is what makes it visible. The vast emptiness of intergalactic space creates the frame that holds Andromeda. The darkness is not nothing. It is the stage. It is the silence between the notes that makes the music. Andromeda floats in that darkness, a solitary island of light. It is accompanied by its small satellites, its entourage of dwarfs, but mostly it is alone. The distance to the next major neighbor, us, is immense. That isolation is part of its beauty. It stands apart, complete unto itself, a self-contained city of stars drifting through the endless night. So when you think of Andromeda now, don't just think of a number. Don't just think of 220,000 light years. Think of the layers. Think of the light fading into the dark. Think of the gravity holding it all together. Think of the deep time that shaped it. Think of the silence. Andromeda will continue to be measured. Its numbers will continue to be refined as our telescopes get better and our computers get faster. Its story will continue to unfold slowly across billions of years as it moves closer to us. But for now, for tonight, it is enough to know this: the galaxy is vast, it is patient, and it is exactly as large as it needs to be. You can let that scale rest where it is. There is nothing more you need to hold on to. The universe is in no hurry. The stars are not going anywhere. The gravity is holding everything in place. You can relax into that stability. You can trust the physics that holds the galaxy together to hold you too. We are all made of the same stuff as those stars. We are all moving through the same space. We are all part of the same vast, quiet system. And in that connection, there is a deep, abiding peace. So let the galaxy expand gently outward in your mind one last time. Let the disk spin slowly. Let the halo fade softly. Let the dark matter hold it all safe. And let yourself drift in the quiet space between the stars.
And so we come to the end of our journey outward. We have traveled a great distance tonight, moving from the familiar ground of Earth, past the veil of our own atmosphere, and across the immense, silent gulf that separates us from our neighbor. We have walked through the bright, crowded streets of Andromeda's core. We have drifted through the spacious quiet of its spiral arms. We have floated in the thin, ghostly mist of its stellar halo.
and we have felt the heavy, comforting anchor of the dark matter that holds it all in place. We have asked how big it is, and the galaxy has answered us, not with a shout, but with a whisper. It has shown us that size is just a matter of how long you are willing to look and how deep you are willing to listen. It has taught us that boundaries are soft, that edges are gentle, and that everything in the universe is connected to everything else by the slow, patient pull of gravity. Now, it is time to turn back. It is time to leave the vastness of intergalactic space and return to the quiet, warm space where you are resting right now. But we do not leave the peace behind. We bring it with us. We bring the silence of the void. We bring the slowness of the stars. We bring the steady, unhurried rhythm of the galaxy back into this room. Imagine the galaxy receding slowly behind you. It does not disappear suddenly. It simply grows smaller, softer, turning back into that faint, comforting smudge of light in the night sky. It remains there, watching over the dark, turning slowly on its axis, content in its own existence. It does not need us to watch it to keep spinning. It does not need us to measure it to keep growing. It will be there tomorrow. It will be there in 1,000 years. It will be there when you wake up. You can let go of it now. You can let the image of the spiral fade gently from your mind, like a dream slipping away in the morning light. Let the stars blur. Let the dust lanes dissolve. Let the darkness of space blend with the darkness behind your closed eyelids. Feel the space around you now, not the terrified vastness of the cosmos, but the safe, contained vastness of sleep. Your room is a sanctuary. It is a small, private universe where the laws of physics are simple. Gravity holds you down, warmth holds you close, and time slows down to a crawl. Feel the weight of your body sinking into the mattress. This is the same gravity that holds Andromeda together. It is the same force that binds the satellite galaxies to their host. It is a universal embrace. It is not pulling you down, it is holding you. It is anchoring you to the earth, keeping you safe, stopping you from drifting away. You can trust it. You can surrender to it completely. Let your muscles loosen. Let your shoulders drop. Let your hands uncurl. There is no need to hold on to anything anymore. Gravity has you. Think about the time we spoke of, the deep time, the millions of years it takes for light to travel, the billions of years it takes for a galaxy to merge. In the face of that scale, the worries of one day dissolve. The tasks of tomorrow feel very far away. They are small. They are manageable. They belong to a different timescale, a fast and frantic one that does not exist here. Here, in the dark, you are operating on galactic time. Slow, steady, deeply patient. There is no rush to sleep. Sleep is like a galaxy. It has no hard edges. You do not cross a line and suddenly arrive there. You drift into it. You fade into it. You pass through the halo of drowsiness, moving deeper and deeper until the waking world becomes faint and distant, like a star on the edge of visibility. Allow yourself to drift. Allow your thoughts to wander like those loose stars in the outer halo. They don't need to be organized. They don't need to make sense. Let them float. Let them be sparse and unconnected. If a thought comes, let it pass like a comet, visible for a moment and then gone again into the dark. Do not follow it. Just watch it go. The silence of space is now the silence of your mind. It is not an empty silence. It is a rich, heavy silence. It is a silence full of potential, full of rest. Listen to the quiet in the room. Even if there are small sounds, the hum of a fan, the wind outside, the settling of the house, let them be part of the silence. Let them be the background radiation of your own personal universe. They are just reminders that the world is still there, turning safely without you, so you don't have to watch it. You have learned tonight that things are often larger than they appear, and that the most important parts are often invisible. Sleep is like that too. It is a huge part of your life, a huge invisible ocean that you sink into every night. It restores you. It rebuilds you. It is the dark matter of your existence, holding everything else together. Without it, the bright stars of your days would fly apart. So honor it now. Giving into it is not giving up. It is connecting to something essential.
Feel the darkness wrapping around you like a soft blanket. It is not cold, it is warm. It is protective. In the dark, there are no expectations. There is nothing to see, nothing to judge, nothing to do. There is only being. There is only breathing. Inhale, exhale, just like the galaxy. Slow, rhythmic, eternal. Your breath is the tide. It comes in, bringing oxygen, bringing life. It goes out, carrying away tension, carrying away the day. In, out, expanding, contracting. You are a microcosm of the universe. The same patterns that shape the spiral arms shape your breathing. You are in sync with the cosmos. You are part of the great, slow dance. Drift deeper now. The bright disk of consciousness is fading. The lights are going out one by one. The core is dimming. You are moving out into the halo. The stars are few and far between here. It is quiet. It is spacious. There is so much room to rest. If you look back toward the waking world, it looks small. It looks like a faint smudge in the distance. It is not important right now. What is important is this feeling of suspension, this feeling of floating, this feeling of being held by the dark. You are safe. You are warm. You are understood. The universe is vast, but you are here, exactly where you are meant to be. You fit perfectly in this moment. You fit perfectly in this bed. You fit perfectly in this sleep. Let the final tensions melt away. Let your jaw unhinge slightly. Let your tongue rest on the roof of your mouth. Let your eyes sink back into their sockets. Let your forehead smooth out. Imagine a wave of relaxation starting at the top of your head and washing slowly down your body, past your eyes, past your neck, down your spine, through your hips, down your legs, all the way to your feet. Washing away the day, washing away the noise, leaving only the clean, quiet, heavy feeling of rest. You are drifting towards the center of sleep now. The gravity is pulling you gently in. It is an irresistible pull, but a kind one. You want to go there. You want to see what is in the deep, dark center. You want to rest in the place where everything is still. Andromeda is sleeping too. The whole universe is sleeping. The stars are burning, but they do it silently. The planets are spinning, but they do it without effort. Everything is moving, yet everything is at rest. You are part of that. You are nature. You are physics. You are stardust catching a nap. There is nothing left to learn tonight. The lesson is over. The books are closed. The observatory is shutting down. The telescope is capped. The lights are off. The astronomer is going home. It is just you now. You and the dark. You and the quiet. You and the soft, slow rhythm of your own heart. Sleep is coming. It is already here. It is settling over you like fine dust. It is filling the spaces between your thoughts. It is weighing down your eyelids. It is slowing down your mind. It is time.
Good night to the stars of the halo. Good night to the spiral arms. Good night to the bright core. Good night to the satellite galaxies. Good night to the dark matter. Good night to the streams of history. Good night to the light that traveled so far. And good night to you. Thank you for joining me on this journey outward. Thank you for being part of the Sleepy Academy. We will be here when you wake, ready to explore again. But for now, the exploration is done. The only journey left is the one into dreams. Drift, float, sink, sleep. Good night.